Simone, lo streaming su YouTube dovrebbe partire fra un po'.
Perfetto, ok, grazie. I saw that Marie-Laurie Frey is online. Hi, Marie, can you hear me?
Yes, I can hear you.
Hi, good afternoon.
Good afternoon.
Okay, I will make you presenter in order to test your share screen. Okay, now you are able to share your presentation. It's only a test for the time in which you will be our presenter.
Okay. Should I see something? Yes, share.
Okay.
Something?
Yes. I see a satellite, Sentinel-3. Okay. Could you try to make full screen the presentation?
Yes, it is in full screen now, at least on my screen.
I don't know, because it's full screen, but
we see the presenter mode now. Possibly you have to change something in your settings of PowerPoint. Yes.
Okay, now it's perfect. Okay.
Change the slides. So
yes, it's moving well.
Great. Everything's works fine.
Everything is working well. Thank you very much.
There is a gray box, possibly is the one from WebEx in the upper left. Not now. Okay, now it's good.
Oh, I stop the sharing.
Yes, please.
Yes.
Great.
Thank you very much.
Thank you.
Hi, Steen. Good afternoon. Can you hear us?
Yes, I can hear you. I just had to unmute my microphone. I'm sorry for being a bit late, but it's been quite busy.
No. You are in time.
At the end of time, sorry.
No,
yes.
You are in time. No problem. Okay, I make you presenter. Okay, now yes. Perfect.
Do you have a gray box in the top left corner again?
No.
Okay.
No.
Because
yes.
I see you as part of my slideshow from beginning. Okay, what do you see now?
It's in presenter mode.
Okay.
Screen.
It's a full screen, but presenter mode.
What's happened?
It's
something strange. Okay, you are unmuted still. Okay, now you are. Okay, now it's full screen. Okay, but you are unmuted. I don't know why.
Yes, do you hear me now?
Okay, now okay. Yes. Now yes. Okay, perfect. Thank you very much.
It looks fine. Do you see my images?
Yes, well, and it's moving through the slide.
Okay.
Thank you very much.
Yeah, thank you.
We have just 3 minutes. Good afternoon, Hossan.
Good afternoon. How are you?
Fine, thank you very much.
So can I share my screen?
Yes, just one moment. I make you presenter.
Okay. Actually, in room 2, I faced problem in sharing the screen yesterday. I was struggling, so I want to make sure.
We'll try now. Now you are presenter.
Okay.
You should be able to share.
Okay. Okay. So can you share? Can you see my screen?
Yes, it's moving very well.
It's moving, right?
Yes, and it's full screen.
Okay. Great then.
Thank you very much.
What I will do actually, maybe the internet speed in my side could be slow, so that's why
No, the speed is well. It's moving with a reasonable speed.
okay. No, so I'll not share my video to save my bandwidth. So I think I will share like this.
Yes, I hope. Also, me, I don't have a very fast bandwidth connection. I hope this. I know this problem. Thank you very much.
Thank you. Thank you.
Okay, Emanuele, I think just 1 minute.
Yes, 1 minute left. I can.
He remains John Bradburn at 15 to 4 p.m., but I think that it's time to begin.
Yes, there is no time to do another try. Yes. Okay, shall we start? Dear presenters, attendees and all, good morning or good evening or good night. This is the last day of MicroRad 2020. Let me recap very briefly, the program for today. We are on Friday now, and we now have the third last keynote. And after the keynote at 2:30 p.m. Central Europe time, after the keynote, we will have in room 1 the first part of the session, sensor calibration, RFI, and spectrum management. At 4:30 p.m., we will have the usual 30 minutes break with the pre-session for the second part of the session, and the sensor calibration, RFI, and spectrum management session will resume at 5 p.m. That's all from my side. I'm now honored to give the floor to Catherine Prigent from the Paris Observatory. She will speak on behalf of the CIMR Mission Advisory Group about CIMR, the passive microwave satellite mission for Copernicus. Dear Catherine, the floor is yours.
Thank you very much. I would like to share my screen. Can you give me the right to share my screen? Okay. Oops. Uh-oh. I don't think I managed to. Oops. I can't move to, oh yes, here it is. Okay, can you see it full screen now?
Yes, yes, perfectly.
Great.
It's screen.
Okay, perfect. Thank you very much for inviting me to present the Copernicus Imaging Microwave Radiometer. My name is Catherine Pridgeon. I work in Paris Observatory with my colleagues Carlos Jimenez and Liz Killick. And it is a pleasure to present the SIMR mission here. SIMR is a result of an extraordinary work these last years from the SIMR project team at ESA, especially from Greg Donlan, and from the SIMR Mission Advisory Group. My connection with ESA is that I belong to mission and science advisory groups at ESA for microwave missions. The outline of my talk will be the following. First, SIMR is a Copernicus high priority expansion mission, and I will say a few words about Copernicus. Second, the SIMR mission requirements will be described. Then I will present the evaluation of the SIMR performances, and I will conclude on the future missions for passive microwave Earth observations in Europe. First, a few words about Copernicus. Copernicus is a European Commission program for the Earth observations. It is composed of 6 different services shown on the right. These services use Earth observation from the Copernicus Sentinel missions. The satellite data are operationally distributed and over the long term with a free access policy. Here are the currently planned Sentinel missions. In green, the 7 Sentinel satellites already in orbit, and the X6, an altimeter, should be launched tomorrow, actually. You will notice that there is no passive microwave mission so far. The Copernicus long-term strategy is to satisfy the European policy and the user needs. For that, the European Commission collects user requirements and prioritizes the need of the services. It is a user-driven process. Then, ESA translates the requirements for observations into space mission requirements. In 2016, the European Commission agreed on an integrated European policy for the Arctic. Actually, the Arctic is a very fragile environment and is a key indicator of climate change. It requires specific mitigation and adaptation actions covering different issues such as climate change or the sustainable development in the Arctic. The poles are particularly affected by the climate change. This is a so-called amplification of the climate change in the Arctic. Here, the air temperature anomalies globally in dark blue, and for the Arctic in light blue since 1850 from the Hadley Center temperature analysis. It shows a significantly stronger increase of the air temperature over the Arctic as compared to the globe. One major consequence of the temperature increase in the Arctic is a reduction of the sea ice extent over the last decades, especially at the end of the melting season. This has been observed by passive microwaves since the end of the 70s. You can see here the annual cycle of the sea ice extent from EUMETSAT OSISAF. The mean value in gray over 1980 to 2000, and the values for the last years in colors. A drastic decrease of the extent is observed, especially in September at the end of the melting season. Another variable very important to observe over the pole is the sea surface temperature. This parameter is traditionally derived from thermal infrared images. On the left, an example of infrared sea surface temperature estimated for a day as derived from multiple infrared instruments. You can see large holes in gray due to clouds. Some areas in the Arctic are persistently cloud covered. On the right, the passive microwave counterpart over a day with a complete coverage of the Arctic Ocean. So let's move to the mission requirements. First, what is the current situation for key parameters over the Arctic? We already saw that the sea ice concentration and the sea surface temperatures could be derived from microwaves under cloudy conditions and at night, in complement to infrared and visible observations. Many studies showed that sea surface salinity and thin sea ice thickness can be derived from 1.4 gigahertz from instruments such as SMOS or SMAP. However, microwave sea surface temperatures and sea ice concentrations are only available at low spatial resolution, 50 kilometers when you use 6 gigahertz, and or with limited precision. There is no guarantee of continuation of sea surface salinity and thin sea ice thickness that depend on measurements at 1.4 gigahertz. SMOS and SMAP will not last forever, for sure. These are the requirements for the user needs for key parameters to be observed. There are very strong constraints on the spatial resolution and uncertainty, especially for sea ice concentration and sea surface temperature, with, for instance, a spatial resolution of 5 kilometers for the sea ice concentration and an uncertainty below 0.2 Kelvin for the sea surface temperature. To address this user needs, a satellite mission design primarily dedicated to observations of the Arctic. This is a Copernicus imaging microwave radiometer. It will provide measurements over 6 hours in the polar regions with no hole at the poles, and it should cover 95% of the globe every day for application to all Copernicus services. It will provide high spatial resolution of sea ice concentration and sea surface temperature, thanks to a very large antenna. It will provide low uncertainty for sea ice concentration and sea surface temperature, thanks to multiple frequency observations and low noise receivers. It will prevent the anticipated gap in capability after SMOS and SMAP. It will be the first Copernicus microwave imager. Copernicus services currently rely on research missions, for instance, for sea surface temperature under cloudy sky or for salinity. This is a new version of a very famous figure from Willite. It shows the normalized sensitivity of the observations for a specific variable as a function of frequency. As a consequence, the primary frequencies that should be used for a given geophysical parameter. Two environments are considered here, mid-latitude and Arctic. Solid line for mid-latitudes, dotted lines for the Arctic. For instance, for the sea surface temperature in orange, the maximum sensitivity is obtained around 5 gigahertz for mid-latitude and at a lower frequency for the Arctic. But remember that frequency selection also takes into account spatial resolution, band protection and RFI, as well as continuity issues. For that reason, 6.9 gigahertz has been selected for simmer. The sea ice concentration in purple, the sensitivity of the concentration increases smoothly with decreasing frequencies. However, do not forget high spatial resolution is required for sea ice and that it decreases with frequency. Sensitivity to sea surface salinity sharply increases at low frequencies, limiting the frequency choice for salinity estimation to the low frequencies. And 1.4 gigahertz is selected. Major instrument requirements are integrated here. Frequencies at 1.4, 6, 10, 18, and 36 gigahertz, high spatial resolution, lower than 15 kilometers at 6 and 10 gigahertz, lower than 5 kilometers at 18 and 36 gigahertz, 55-degree incidence angle, and backward and forward views. At least dual polarization, V and H. FOAS should be larger than 1,900 kilometers. It will be a sun-synchronous orbit at 6 dawn and dusk, similar to SMOS. The orbit should maximize collocation with METOP SG in the Arctic, and there shouldn't be any hole at the pole. This implies a very large rotating mesh antenna between 7 and 8 meters, multiple feed horns for most frequencies, low noise receivers, and RFI mitigation strategies. Actually, the industry selection took place very recently, and the contract for phase B2 was signed just a week ago. You can see here an artistic view of the instrument. Thales Alenia Space will serve as mission prime. The main partners will be OHB in Italy for the instrument and HPS in Germany for the large deployable reflector. Note that there are still very little details available about the final instrument design. Here is a table of the radiometric requirements for SIMR as compared to previous instruments like SMAP and AMSR2. For instance, for the 6 GHz that is crucial for sea surface temperature and sea ice concentration, SIMR provides a much better spatial resolution with a ratio of approximately 3 and an improved NE delta T. This is an animation of the SIMR orbit. It provides global coverage of the Arctic within a day. There is not to be holes at the poles, and it will provide 95% coverage of the globe also within a day. The SIMR capacity to provide the major Arctic parameters has been evaluated. A science end-to-end simulator has been developed. It is based on the mission requirement document and from some hypotheses on the instrument implementation. It is the result of a collaboration between different groups mentioned here within an ESA contract. First, geophysical fields are generated with all the relevant surface and atmospheric information to feed a radiative transfer model. The forward model accounts for the interaction of the microwave radiation with the surface and atmosphere under the instrument observing conditions such as frequency or incident angle. The instrument simulator convolves the antenna patterns of each feed horn with the brightness temperatures and adds the instrument noise. The retrieval algorithms are applied to these simulated brightness temperatures, and the resulting geophysical parameters are then compared to the initial surface and atmospheric fields to evaluate the mission requirements. Here are the major characteristics of the instruments used for the end-to-end simulator. They correspond to the preliminary phase of the project and can slightly differ from the final instrument. These characteristics correspond to an antenna of the order of 8 meters. Antenna patterns were provided by ESA for the calculations. For each frequency, the number of horns is indicated along with the footprint size or the NE delta T. Over ocean, the brightness temperatures have been simulated using an available radiative transfer model from Meissner and Wenz. On the left, the inputs to the model. In the middle, the simulation results for all SIMR frequencies at V-pole. And on the right, the comparisons with collocated SMAP and AMSR2 missions. Systematic comparison has been performed with real observations to ensure the realism of the simulation. This is very important. As you can see, except under severe weather, good agreement is obtained. An optimal estimation has been developed to retrieve consistent ocean and atmospheric products using all SIMR channels. Here, you can see the theoretical error estimates for winter Arctic scene. You can recognize Greenland, Svalbard, on the north of the Scandinavia. On the left, the sea surface temperature fields. In the middle, the estimated temperature retrieval error from SIMR, and on the right, the corresponding error for AMSR2. These are theoretical errors, I remind you. With SIMR, there is a strong improvement in the spatial resolution thanks to the large deployable antenna and a strong improvement in the retrieval precision, even for cold waters, thanks to the low noise receivers. Further evaluations have been conducted with the end-to-end simulator. The maps show the retrieval errors for SIMR on the top and for the SMAP and AMSTER2 combination on the bottom. The distribution of the errors is shown on the left for SIMR in blue and for SMAP and AMSTER2 combination in orange. It confirms that the uncertainty requirement below 0.2 Kelvin can be met globally. For sea ice, the existing emission models are very difficult to apply on large scales, and an original and pragmatic emission parameterization has been developed. Here you can see simulations at the top and AMSTER2 observations at the bottom at 18 GHz for both V and H polarizations. For the Arctic winter on the left and for the Antarctic winter on the right. Comparisons of the simulated brightness temperatures with the coincident AMSTER2 observations shows the realism of the simulations for both polarization and both poles, which is very difficult to achieve when simulating sea ice responses. Note that similar results are also obtained for the other frequencies. The classic sea ice concentration retrieval using 18 and 36 GHz has been tested for both poles for winter and summer seasons. The true sea ice concentration on the top, the retrieved values at the bottom, with good agreement for both poles and seasons. For better quantification of the uncertainty in sea ice concentration, these are the histograms of the retrieved ice concentration at 0% on the left and 100% right for the 4 previous scenes. Arctic on the top and Antarctic on the bottom. The retrieval errors are indicated in blue. It is always below 5%, which is a SIMR requirement for SIC. Summarize the presentation so far. SIMR is a new multi-frequency high-resolution microwave imager dedicated to the Arctic. Performances have been successfully evaluated with an end-to-end simulator. SIMR triggers new retrieval developments, not only for sea ice and ocean applications, but also for land surfaces, such as snow water equivalent over land, soil moisture, vegetation properties. These have not been shown here for the sake of time. The implementation phase of SIMR just started last week. And SIMR is one of the 6 Copernicus high priority expansion missions. Here are actually the 6 Copernicus high priority expansion missions. CO2M, an imaging spectrometer for atmospheric CO2, CRYSTAL, an altimeter for the poles, SIMR, LSTM, a high resolution thermal infrared radiometer, CHIME, a hyperspectral imager, and ROSEL, an L-band SAR. Synergies are expected between SIMR, CRYSTAL, and ROSEL for the Arctic studies. For instance, SIMR will measure the ice thickness for thin ice and CRYSTAL for thicker ice. This is a view of the ESA Earth observation missions up to 2030, including the Earth Explorers, the Copernicus satellites, and the meteorological satellites. The dotted red circles indicate the passive microwave missions so far, the atmospheric sounder onboard METOP, and SMOS. But what is the future for passive microwaves? New sounders and imagers on board METOP and SIMR among the 6 priority expansion missions. This looks like the beginning of a golden era actually for passive microwaves in Europe. So far we had AMSU and MHS sounders on board METOP and the SMOS mission. In the years to come, we will have an improved microwave sounder on METOP A, 2 imagers on METOP B, with the very first operational imager at sub-millimeter frequencies, IC, the ice cloud imager, and with Copernicus, we will have SIMR. This is the atmospheric capacity at Venice as a function of frequency between 1 and 700 GHz. SIMR will cover the low frequency range for surface applications. The MWI imager on board METOP B will cover up to 190 GHz, both in window frequencies and in water vapor and oxygen lines. MWS, a cross-track sounder on board METOP A, will provide channels up to 230 GHz for temperature and water vapor profiles of the atmosphere. And finally, IC on METOP B will cover the millimeter and submillimeter range up to 664 GHz to analyze the cloud phase. All these instruments will provide unprecedented coverage of the microwave spectrum for Earth observations for a very broad range of applications. This is an extraordinary opportunity for the passive microwave community, especially for our young colleagues. Expertise in microwaves will certainly be needed in the next years to develop all these instruments and then to fully exploit their observations. We can really expect a growing success of MicroRad in the next years. Thank you very much. And you will find much more information about SIMR on the website mentioned here. Thank you.
Thanks a lot, Catherine. It was a very nice and interesting presentation, which gives the outlook for the future years, for, as you said, for the young scientists, which are going to benefit at most of these improved sensors. Any question or comments from the audience? I remind you that you can unmute yourself by your own.
Good afternoon, Catherine. This is Marian Klein with Boulder Environmental Sciences and Technology. I'm curious if you have any estimate on the cost of this mission.
Actually, it is on the Thales website, so there is some numbers given there. It's around 400 million for the first part of the contract that we're talking about.
Thank you.
The official information on the Thales website.
Thank you very much.
Hi, this is Nemesio from CESBio. Catherine, nice presentation. When do you think the size of the antenna will be decided?
It is decided, but the problem is that the contracts have been signed last week and I don't have the information.
Yeah, I mean, you wrote 7 to 8 meters.
Yes. Yes. And when we did the end-to-end simulator, it was not the final version of the instrument, so I can't tell you.
Thank you.
I don't have the information, unfortunately. It will be circulated soon, I believe.
Marco, we have a question from YouTube.
Okay.
It has been reported on the chat.
I cannot see any.
The question is from Xiu Zhan of the NOAA Federal. Land data at level 1 and or level 2 from SIMR will be available freely to global users as ocean data, right? Thanks.
Yes. Yes, all the Copernicus data are available openly to everybody, so they will be available. This is the policy of Copernicus program.
Giuseppe Virone, CNR, I have a question. Also, thank you for the presentation. We were involved in the AB1 design phase of SIMR, and my curiosity is in the framework of your simulations, having an antenna of 7 meter or 8 meter, does it make a big difference for your results?
Actually, it depends about how the antenna is illuminated and how it is built. What matters are the antenna patterns on the ground. So we had several designs to play with, and actually it really depends upon the feed horns, or they are located within the antenna. So it depends on different aspects of the antenna development. But of course, I mean, if the antenna is smaller, you should have a lower spatial resolution. But there is the relationship is not that direct.
Yeah, but I may formulate the question in a different way. A difference in 10% of the spatial resolution, does it make a big difference for the science? 10%, 20%, I mean, in spatial resolution.
It does for some application. The user requirements were very stringent in terms of spatial resolution for products that has sea ice concentration, for instance. So the requirements were very strict there.
Thank you very much.
Any further questions? Oh, go ahead.
Yeah, it's Frank. Thanks for the nice, very nice and effective presentation. Just a curiosity and information. Is in the phase B2 and the subsequent phases, is there the possibility that the number of channels could be put in a discussion, in a sense that can be reduced, or this is set for the mission?
To my understanding, but I'm not at ESA.
We all know that in space missions, this is something, you know, up to the...
Yeah, to my understanding, it's more or less frozen, but I can't answer this question really.
Okay. Okay. Thanks a lot.
Last question or comment? Okay, so if you don't have any more questions, I want to thank a lot, Catherine, for this very nice overview of the mission. We will look for sure in the future for the development, likely in person at next IGARTS. We all keep our finger crossed and we knock wood. So the next session, which is the first session on sensor calibrations and RFI and spectrum management, will be shared by myself and also from my colleague Ada Vittoria Bosisio, that you can see here. We have eight papers, so I'm going to move quickly with the first one, which is going to be given by Mandy van der Vliet, reconciling flagging strategies for multi-sensor satellite soil moisture climate data records. So Mandy, you have the floor. Go ahead with the presentation.
Can you see my screen?
Yes, sure. Go ahead.
Good afternoon. My name is Mandy van der Vliet, and I'm going to tell you indeed about the work we did on reconciling flagging strategies for multi-sensor satellite soil moisture climate data records. So for any long-term climate study, you need, of course, a time series that is long enough and that is consistent. For soil moisture, there's not a single satellite sensor that covers the full global climate record. And therefore, you need to merge multiple satellite sensor products to produce a climate data record. So for the past decade, several studies have focused on how to properly merge these different sensors. But to the best of our knowledge, no research studies have really devoted attention to flagging inconsistencies in this context. So reliable soil moisture retrievals from passive microsatellite sensors are limited during certain conditions, like snow coverage, radio frequency interference, and dense vegetation. For all these cases, the retrievals can be masked using flagging algorithms. But if any of these sensors uses its own flagging system, it can lead to inconsistencies in data availability, leading to visual breaks in climatologies and anomalies. Here we look at a new flagging method that focuses on snow and frozen conditions and can be applied on sensors from 1978 onwards directly by looking at the brightness temperatures, and therefore provide a consistent and model-independent way of flagging. So this presentation consists of two parts. As there's not really an overview yet of the flagging differences, the first part focuses on reviewing flagging differences and impact in context of the ESA CCI soil moisture datasets, and this forms the base for the design and evaluation of a consistent flagging strategy. If you want to read more, then please look at this paper that was recently published in Remote Sensing. In this figure, you can see an overview of the total number of flags per flagging category, and we distinguish between critical flags. This is here defined as a flag that is used by the dataset producer to determine whether the retrieved soil moisture value is not considered appropriate for dissemination and hence is replaced by not a number, or advisory flag that is defined as a flag that indicates that a data value should be treated carefully and can be filtered out by the user. As you can see over here, we compared two single sensor datasets of SMOS and SMAP, and also the multi-sensor datasets of CCI. And we can see the differences plotted over here for the critical by the opaque color and the advisory by the more transparent color. You can see that most of the highest number of critical flags are actually in the snow frozen category, with 11 out of 31, which is 36%. The next figure demonstrates the differences in data source types per flagging category. So here we distinguish between internal only, so really based on the satellite signal itself, the green color, and the external data source types, the blue colors. And yeah, when it's another satellite, when it's a model that's used, or when it's a mixed data source type. What you can see over here, that there is some model dependency in the topography, in the urban area, in open water bodies, and in the snow and frozen flagging. And that most of the most different type of data source types are there in the snow and frozen category. We also considered the impact of these differences on the data availability by considering the total flagging intensity. This is here defined as the mean of the total NANS in the soil moisture record, and then we consider the level 3 of the data sets. So you can see the result of this in this figure. You can see it spatially plotted and also over the latitudes for the different seasons. What we can see by comparing the two single sensor datasets, SMOS and SMAP, you can see that there are similar patterns detected, but also quite some differences in the variability in the number of in the flagging intensity. And also, if you look over the latitude, so we can see that in the tropics, in South America and Africa, there's a bit more flagging for SMOS on the data availability. We also see that in the latitudinal plots, and we can see that most of the non-availability or the highest total flagging intensity is because of critical snow and frozen flags, which is 64% for SMOS and 78% for SMAP, relatively. So now we saw that the highest number of critical flags, but also the model independency and the highest variety in data source types, and the highest impact on data availability was for the snow and frozen category. We actually focused on designing and evaluating a consistent flagging strategy for these conditions. This is based on Yin et al., and you can see the decision tree over here. We validated this against 399 stations of in situ measurements from the ISMN network of snow and surface temperature. And the first threshold that you can see over here is actually a contrast between high frequency and low frequency in brightness temperature, which is dependent on relationships between the brightness temperature, the unbounded water molecules, the dielectric constant, and volume scattering. We also try to distinguish any scattering effects from heavy precipitation by including the other threshold, which we found by looking at time series of precipitation in Canada and Europe. And we found an anomalous pattern over Greenland, which was also found in other studies. And yeah, we made sure that we also covered Greenland well in terms of the more difficult, complex situation of ice layers there by adding this threshold. So if you look at the performance metrics, then we compared the cumulative snow, ice, and frozen flags of the two single sensor data sets against also the new method, but then applied on EMSR2. And they were all validated against snow water equivalent and surface temperature from the ISM stations. We looked at two different types of threshold conditions, so the lighter snow and frozen conditions and the more heavy one, T1 and T2. And we considered the FDR, the false discovery rate, where you're really looking at the false positives. Then the FOR, the false emission rate, looking at false negatives, and the accuracy, looking at the true positives and true negatives. So what we can see from the FDR is we can see that the cumulative snow, ice, frozen flag of small soil moisture is overflagging compared to the one for SMAP and EMSR, the new methods on EMSR2. We can see for the FOR for both threshold conditions, and also regarding the FOR, we can see actually that SMAP and EMSR2 are relatively more underflagging compared to SMAP for both conditions. And if we consider the accuracy, then we can see that SMAP is performing slightly better than the new method EMSR2. And we can also say that the new method EMSR2 is quite comparable, although a bit less performing as the one for SMAP, but it is model independent and can be applied in a consistent way to all the satellite sensors. Then we're going to the take-home message. So in the first part, we looked at the differences in the flagging systems. So we looked at the number of critical and advisory flags. We looked at the data source types, and we looked at the impact on the data availability. We saw that there are quite some differences here. This should be really considered well if you're going to merge these data sets that we use in this study for any climate study, because it can have an effect on both the seasonal and annual statistics. Then for the second part, we looked at can we design a strategy that is consistent and can be applied on snow and frozen conditions, for which we found the most differences. And we found a method that is robust and can be applied consistent and more independent, although it can still be improved, of course. So the main limitations and recommendations. So this flagging method can be applied only when you have the frequencies that were used in the thresholds. So not for sensors that only have, for example, L-band. And if you want to use the data of another satellite sensor for that day, you have to consider the effects of different footprint sizes, shapes, and different acquisition times to be sure if you can do that. We also recommend to extend this flagging to more conditions, also considering the bare ground, deserts, heavy precipitation, dense vegetation, open water bodies. And to extend assessment by including active and other passive submerged sensors, also including ground networks on the southern hemisphere, if they're available, and a focus on seasonal variations in performance. So with that, I wanted to end this presentation, but questions are very welcome, and thank you for your attention.
Any question for Mandy? Comments? I have just one question. Actually, it's more a curiosity. Do you think that an action at space agency level to harmonize the flagging, I don't want to say that all of the agency has to produce the same, has to use the same flagging, but produce on a site also a common set of flagging. Such flagging can be useful for the community, and harmonized flagging can be useful for the community or not?
So to understand your question, you mean that next to the own flagging system, you have one set that is common for all the
yes, exactly. JAXA, ESA, NASA can produce a common set of flagging beside obviously the one that they have already developed.
Yes, so I would of course really recommend that. I think that would make it much easier, because I think one thing I didn't say, it was quite difficult to really find out what are all the different flags involved for each of the data sets, what are the data source types, what is happening exactly, which thresholds do they take for the critical, which one are critical, and how can I get that out of the data? That is quite difficult, and you have to go to a lot of documentation for each of the sensors. So now I did it only for the 2 single sensor datasets and for the ESA swimmerture dataset. And I think if you want to do it for more datasets, etc., it would be very beneficial if there would be also a common flagging system that leads to a harmonized way of flagging.
Okay, thank you. Any more questions or comments? Okay, if we don't have any more questions, so thanks, Mandy, for your talk. And we move ahead with the next presenter, which is Sten Savstrup Christensen, and is going to talk to report us about the monitoring of Arctic sea ice using the DTU L-band radiometer MicroRad early result and RFI analysis. So go ahead, Sten. You are muted.
Whenever I start sharing my screen, it mutes me. I don't know why. Do you see the presentation mode now?
Yes, yes.
Thank you. Yes, let's go. Okay. The objective for this presentation that led to this presentation was the originally the ESA soil moisture and ocean salinity SMOS motion, which has been presented several times during this conference, so I'll not dwell into it. But one of the products that has been produced is sea ice thickness, or thin sea ice thickness up to 1.5 meters, and a chance for validation of this by in situ measurements. And by measurements, I mean the DTU L-band radiometer, MicroRad, and some additional thickness measurements by in situ people, scientists, was the MOSAIC campaign, which has been developed some years ago and was run throughout the last year and a bit more. And just to show you what that is about, then it was the German research icebreaker Polarstern that set sail from Tromsø, spent a year drifting through the ice in the Arctic Ocean, and the purpose was to make a breakthrough in understanding of the Arctic climate and all of that. And on the map here on the right, you see in gray the actual path of this sailing and transit sailing by Polarstern, and on the left, and that's the gray curve, and the drifting within the ice is the blue curve. More details about the MOSAIC expedition can be found on this homepage here, and I would like just to stress that everything on this page is taken from that homepage, just to make that clear. MicroRad was installed on P deck on Polarstern, and for those of you who have not seen a ship, an icebreaker like Polarstern out of its most natural environment, I have here some photos from the installation the spring last year, where we did some test installation of Polarstern up here to the left on top of the bridge called P deck, where we are approximately 18 meters above sea level. And we tested that we could see the sea and that we could have the elevation angle requirement, and that we could connect to ship power and intranet. You see the actual installation slightly later on this image down right here. And for those of you who have not seen how big a ship actually is beneath the water, smaller, not like an iceberg, but somewhat, what you see here is the bottom, and it's the small figure standing there at the rudder is actually me. Just to brief talk about MicroRad, it's obviously L-band, as that is the frequency of SMOS. It's fully polarimetric, EI the 4 Stokes or modified Stokes parameters as SMOS. In addition to that, we have fourth order movements calculated online for offline detection and data discarding using based on this kurtosis. In addition, I would like to mention that we also on MicroRad has 4 spectral subbands in addition to the full bandwidth product. The main reason for that is to do some cross-frequency RFI detection and subsequent data discarding. You may ask why not more than 4? That's because the instrument is almost 20 years old, so that was what could be done almost 20 years ago. In order to make this installation, we unfortunately had to do a major refurbishment of MicroRad. It was originally designed for most likely air or ground-based campaigns under nice conditions, and therefore we had to build this, as you see here on the right, a big box for insulation. It is not, for L-band, it's not feasible. We considered it not feasible to include the horn in the insulation. So the horn is, as you can see, protruding out of the box, thereby having the temperature of the environment, and that also includes the OMT, auto mode transducer, which produces the 2 polarization and is inside the box, cannot be seen here. In addition to that mechanical refurbishment, we also had to do a sort of operator refurbishment. The original design required a full-time operator turning on the instrument, operating, turning off, doing backups and testing and verifying that everything works as it should. That had to be turned into a fully automatic operation, meaning a computer doing all work. We succeeded almost, but we have some lessons learned, I'm afraid to say. I'd just like you to take note that this is the 150-degree elevation position, which is used for sky cradle, which I will address in a few slides. For total calibration of MicroRad, we have some internal sources. That's a noise diode for fast switching. We have a hot load, which is basically just a termination at a stabilized environment temperature, and we have a cold load, which is an LNA input. For external calibration, we use LN2, as shown in this image, and a sky view. This is one of the complications you encounter during campaigns. The image shows the post-campaign calibration where I went alone and had to stay in quarantine for a week to get corona clarification. And then these 2 transport boxes put on top of each other made the table. And behind the control computer laptop, you can see a green LN2 container, which is actually the tool used for liquid nitrogen calibration of MicroRad. I should say that outside this LN2 calibration is the auto mode transducer and the antenna horn, 2 bulky and passive, both passive but bulky and mechanical structures, therefore extremely stable, and we have throughout the campaign measured their physical temperature. And the inside of the insulated box can be seen in this photo. Just before, now, I have 4 minutes left. I'd like to show some of the results. The first one we did was in Tromsø, where we did the final installation before the campaign started. What you see in this graph here to the left is a comparison between a model and a measurement of the sea surface temperature at the 2 polarizations at different incidence angles. And if you compare with the model, I believe it's Klein-Smith, you see that the V polarization, the first modified Stokes parameter, fits very nicely, while the H, which is the one at the bottom here, deviates significantly for temperature for incidence angles above 50 degrees. And the reason is shown in this image here. This is the position, and when the incidence angles becomes like 50 degrees or above, then we see a significant part of the mountain on the other side of the Tromsø Sound, so we could not use those data. Otherwise, it shows that MicroRad is accurate within 1 Kelvin, at least accurate within 1 Kelvin of the model. Now, for the last few minutes, I would like to present some of the very early results that we have. I should say that we should have 1 year of data, and it will amount to about 10 to 12 terabyte. Unfortunately, not all data is available yet. I checked yesterday, so I'll have to download later. Also, there are some gaps in the data due to power failure on the ship, some instrument failures or problems turning the instrument on after power failure. And of course, I also have to acknowledge that the scientific crew on the ship were extremely loaded with work and couldn't attend to all the issues that were with each instrument all the time. So, thank you for their support in trying to get MicroRad work. We had no operators from D2 available. So we had to rely on scientists to do all the work on our behalf. We are not done much on processing. Time has not been available, but we still need to assess for RFI and quality, and that's where we have started. On this figure to the right, you see the sky calibration average brightness temperatures. And I must stress this is extremely preliminary processing. We just try to do a default scaling for brightness temperatures, which is obviously wrong, as the horizontal polarization brightness temperature is consistently negative. There's also some significant fluctuation here, and that could be due to several problems. One of them is identifying sky view data. That was not automatized registration, so we need to verify that. Also, I should say that these data are not yet compensated for internal temperatures or antenna horn physical temperatures, so they may change significantly. Next, here is the first data. They are from the Barents Sea. We could not measure in neither Norwegian nor Russian territorial waters, so there's a few hours in the Barents Sea. And what you see in the top left is the VNH brightness temperature, or rather counts. I gave up default calibration to avoid presenting erroneous brightness temperatures. And what you see here is the typical recording sequence, which is 4 minutes of data, ice or water in this case, half a minute of the active cold load, half a minute of the hot load, and then continue with data. Remember that we are supposed to have a fairly stable target in this situation, so it makes sense to have long times for calibrations as well. For the third and fourth strokes, you see here at the bottom left, and what is quite interesting is to see that you have a significantly higher variation when observing the target at sea than the calibration target. Also, for fourth strokes, which is a bit surprising, there shouldn't really be any fourth strokes, but apparently variation is greater for measured than calibration targets, and that's one of the things we have to look into. On the right here, you see kurtosis, also raw data. You see kurtosis should in theory be 3, and it should be independent of amplitude, but the recording sequence shows that this is not the case, and we mainly believe this is due to the fact that we have a limited bit width and thereby some quantization, and that affects the actual estimated kurtosis value. You also have some significant examples of RFI here, showing that we also need to do that filtering. I'll go very briefly through the last of my slides here, where I just show some examples of what we have of kurtosis maximum within each second, and you see some peaks here when it transits. When the recording transits from one mode to the other, which is not surprisingly, but also a lot of RFI in between these transitions. So even in the Barents Sea, there's RFI, and we have to filter that out. And with that, I will conclude my presentation and hope to be able to present more results in the future.
Thanks, Dean. It was really a very interesting presentation.
Thank you.
At least I think it was really an effort to work in such an environment. Any question for Steen or comments?
I have a question. So Steen, thank you very much for the preliminary results. So this looks very encouraging. I just more have a comment. You mentioned this sky calibration and the timing of the sky calibration. This was sometimes a bit difficult to look on the watch and write this down. So I think automatic identification will probably help to get better results there.
Yes, I fully agree with you, and we are pursuing that. Unfortunately, it's not easy because there seems to be a long-term drift in the parameters of the instrument, so that we have to set a time-dependent threshold. I'm afraid, sorry to inform you about this, Lars. I know you want more data as soon as possible, but it's not easy, and there's a lot of work to be done. But we're pursuing as fast as we have the time to do it, and I fully agree with your comment.
Thank you.
And I also like to re-stress that Lars was one of the scientists on board who did a large effort to actually make all this possible. Thank you.
Any more questions?
This is Janne Lahtinen from Hub Technologies. Hello, Steen, very nice work.
Thank you.
I just have a comment or a question. Did you consider in the third and fourth Stokes parameters that you are there is seemingly something? Did you consider that it could be due to crosstalk?
Not yet. I think there could be some crosstalk there. I agree with you, but that you mean crosstalk in the antenna, of course, because that's outside the calibration loop. No, we haven't looked into that, but yeah, it's an idea. But why should crosstalk produce higher variation between when you're recording the C than when you're recording calibration targets?
I mean, crosstalk from vertical and or horizontal to T3 and T4. You have some calibration internal, but maybe that doesn't correct everything.
It obviously does not. And obviously you could have a temperature offset. That's not surprising. I mean, the offset you see here could easily be due to lack of calibration. These are not calibrated data, but I'm more concerned why I have this high. The variation seems to change between calibration target and sea surface target in this case. But any idea would be welcome. So thank you for the proposal, the idea. Yeah, absolutely.
Okay, if you don't have any more questions, sorry.
Hi, Steen, this is Joel Johnson. Nice work. Very nice to see these results coming. I was wondering, could you say a little bit about the scene the radiometer is looking at that's adjacent to the ship and how you expect that to vary over time?
Yeah, that's a really good question. We haven't looked into that yet. I know there are some photos, and so that will also be some of our work. In this case, it's fairly easy. It's just the Barents Sea. And it's just 1 hour, so I guess we could look up the meteorological situation. There's no ice here, but in the real world, throughout the campaign, there were ice. Occasionally, there was a Russian icebreaker in our view, and so on. But for most of the time, it was simply just sometime, at least most of the time, should have been undisturbed ice. And I know from Lars, he could probably comment also that they tried to do some ice thickness measurements, and they have taken some photos. And I've seen a few of those photos, and that's why I wondered why I got news about the Russian icebreaker being there, because we were really worrying about the temperatures that our instrument had produced. And I don't know what a Russian icebreaker is emitting, but it's not really scientifically relevant, at least. No, I cannot comment in more details yet, Joel. I'm sorry. We simply don't know yet. We are embarking on a huge work, and it'll take time. I'm sorry. Thank you.
Okay, thank you. Thank you.
Okay, thanks a lot, Steen. We are running out of time, so we have to move ahead. with Giuseppe Virone, which is going to present the thermal vacuum cold target for METOP SG microwave imager. Giuseppe, you have the floor.
Good afternoon, ladies and gentlemen. So, can you see my screen, full screen?
Yes, go ahead.
Very good. So Luca Salghetti and Tito Lupi already presented the NWI instrument on board of METOP SG. So I will just remind that it is a conical scanner. And here you can see very briefly the onboard, the calibration target, and the cold sky reflector, okay, which will provide the hot and the cold references on board. As probably everybody in this conference knows, the verification of performance of satellite before launch is crucial, and it is generally performed in thermal vacuum. Okay, so this is the MWI here in purple in the thermal vacuum test setup. And you can clearly see in here, this is the cold target, and this is the air target. Cold target will operate in the order of 80 Kelvin, whereas the air target here will mimic the scene temperature, operating from 80 Kelvin to 335 Kelvin. In this presentation, we will focus only on the cold target. These targets, both of them and also the ambient targets, are being developed by a completely Italian consortium, which is led by OHB Italia. There are two consultants, Professor Mandolesi, one of the PI of the Planck mission, and Luca Valenziano. And then we have the Cryotech, which performs the cryogenic and the overall thermal design and manufacturing. CNR IT is our institute, which works on the RF design and coordination of the RF measurements. Politecnico Torino and Milano Bicocca for the RF measurements on the absorber, and then Pasquale Microwave System for the manufacturing of the tiles. This slide presents the mechanical structure of the cold target. The surface size is in the order of 0.8 meter times 0.6 meters. So as you can see, it's quite a big target. And the yellow part represents the baffle, which is used to prevent thermal energy from the thermal leakage from the chamber to the target, and to reduce the overall thermal gradients on the surface. The surface is depicted here in dark gray. The heat exchanger, which provides the 80 Kelvin temperature, constant temperature, is on the back of the surface. The emitting part of this black body is like a lattice, a periodical structure composed of pyramids. The pyramids have an inner core of aluminium, in order to keep to reduce the gradient, and a coating of EcoSorb CR 117. Which is a material already used for Planck, and actually the material selected by the manufacturer of the tile, Pasquale Microwave System. The design is more or less, the pyramid size is about 9 millimeters, and the aspect ratio is 4:1. As far as the RF is concerned, RF part, we did a complete characterization of the EcoSorb material, a very accurate characterization by putting bricks of the material inside waveguides at all bandwidths from 18 gigahertz to 180 gigahertz. We did both ambient temperature and cryogenic temperature, thanks to the facility of the University of Milano Bicocca with Professor Mario Zannoni. We did then this was used to achieve the data for the simulation. We did the design on the basis of this data. Then we manufactured the tiles and did free space characterization, both monostatic and bistatics in the full bandwidth of the target. And as far as the tile measurement is concerned, we also did the measurement with the submerged tile submerged in LN2, in order to characterize the emissivity, the reflectivity of the tile, also at cryogenic temperature. But actually, the focus of this presentation is on the computation of the brightness temperature of the target, because as I have shown before, the target is quite big, and the thermal gradients, both on the transverse surface, on the surface of the target, and on the longitudinal part of the target, which is the pyramid axis, these thermal gradients cannot be avoided. Okay, so in order to get an accurate evaluation of the brightness temperature and to satisfy the requirement, we did thermal analysis, complete thermal analysis, considering a three-dimensional surface of the target. Then we did RF analysis, full wavelength RF analysis based on a periodic cell approach. We presented this during the last edition of MicroRad with my colleague Ada Bosisio. Now, the important point is that we developed a multi-physics code which is able to merge the physical temperature with the power, with the field distribution on the pyramid. Okay? And in this way, we get a distribution of brightness temperature over the surface of the target. I will not spend too much time on this. Our approach is like considering the pyramid as a cascade of attenuators with different temperature. So actually, it's actually very easy. And our equations are exactly the same. We derive the same equation that Professor Murk from University of Bern has in his paper. So actually, we have also good agreement with him. And in the end, once the brightness temperature along the test surface is computed, we just have to compute the antenna temperature by weighting the brightness temperature to the antenna pattern, which is given by grasp analysis. So this workflow here is an example of this calculation is in these slides. This slides reports the physical temperature. Okay, we had 7 computation nodes for the thermal model in the pyramid, as you can see here, and these are the results. This is the bottom of the pyramid. This is the tip, and all the thermal nodes are presented here. So you have in some region of the target you have a gradient of about 5 degrees. In other region you have a smaller gradient. Okay. But the good news about this is that if you have a look at the RF power, and we use reciprocity, so we actually radiate from the tip and to compute the electromagnetic field inside the pyramid. The good news is that the RF energy is absorbed just in the middle of the pyramid. As you can see, this is the RF power from the tip. There is only a small attenuation in the tip part where the gradients are big. Okay? So what we can expect, or also already from this picture, and this is what we obtain with the calculation, the good point is that this region of the target, which is colder and closer to the temperature of the base plate, has a larger effect. This is actually the calculation at 18.7 gigahertz. This is the average temperature on the target surface, 0.6 meter times 0.8 meters. And this is the brightness temperature map that we compute, which is a little bit colder than the average temperature. So it's not close to the maximum temperature, but it's actually quite close to the average temperature. Another good point here is that the antenna pattern is not centered on the maximum of brightness temperatures. Is just centered in this region, okay? And this occur this effect is even larger at higher frequencies, 180 gigahertz, where you see that the brightness temperature is even lower, and the antenna pattern is even more offset from the center. Okay, so when we integrate the antenna temperature, we compute the antenna temperature by doing the proper integral, we get this curve. Okay, and this curve tells you that the brightness temperature of our target is higher at lower frequencies and lower at higher frequencies. And sorry, I just let back a few slides. And this happens because the lower frequencies are absorbed more closely to the tip, whereas the higher frequencies travel better to the center of the pyramid, and this, which is colder. And this is the reason why we get such a frequency behavior. Of course, what we did was not only to compute the nominal value, but to perform uncertainty analysis. So we did a quite large variation on all the parameters in the thermal model. We did convergence check on the thermal analysis. We did 10% variation for the absorber parameters, and also convergence analysis on the electromagnetic model. And by doing RSS, by summing up all the errors, we get uncertainty bars of plus minus zero, in the order of plus minus 0.16 Kelvin on each point. Okay, as you can see here. So actually, I mean, what is from this plot? It should be noted that the frequency behavior, I mean, the reduction of the brightness temperature in frequency, which is about 0.7 Kelvin, is larger than the RSS. It's larger than our uncertainty bars. Okay, so this work of characterizing the systematics of the target actually gave a good description of the target that could not have been possible otherwise. So I can just conclude my talk saying that we did with development of TVCT was presented. We did characterization of RF. We did multi-physics modeling in order to deal with such big thermal gradients. We did gradients in the order of 5 Kelvin, but actually the offset between the base plate temperature, which is 78 Kelvin, and the actual temperature of the target is less than 1 degree. Other targets are also being developed, the ambient cold target and the thermal vacuum target. We will use a similar approach, but this target also has quite a big mirror, and this makes the computation a little bit more complex, but it's on the way. So thank you for listening.
Thanks, Giuseppe. We have time for one quick question.
Al Gashevsky, I've got a quick question. Did you account for the reflectivity of the target? And I'm wondering how you would have determined that. Yes,
sorry, I didn't mention it. We actually, yes, I also have a slide for this. I just remember that I have some backup slides. We do both simulation and measurements of the reflectivity of the target, and as you can see, this is in the full band, and as you can see here, simulation value is definitely very low, below -40 dB, and this just goes up here a little bit because the simulation accuracy gets a little bit smaller at higher frequency, but for the measurement we get everything below -40 dB. But in the nevertheless,
very good.
Thank you.
Yeah, thank you.
Okay, it's time to move on. Thanks, Giuseppe.
Marco, you have a question from the chat.
Okay, from the chat, Huang asked for Giuseppe, what is the maximum thermal gradient in the cold target? The antenna pattern used in the TVAC test is near field or far field?
Okay, so the maximum thermal gradient is it's 5 Kelvin, but actually it occurs in this region. So where the antenna this pattern is really small. In the inner part, I don't have the picture for it, but in the inner part, in this region, we get about 4 Kelvin for the. But the good point is that actually, when you compute the brightness temperature, you actually get just 1 Kelvin above the 78, which is the reference. For the near field pattern, yes, this is near field pattern computed on the surface. But what we know, we tested is that actually the longitudinal component of the field is very small, and also the phase curvature is very small. I mean, actually all pyramids see a plane wave with the same angle of incidence. We tested with the grasp analysis, and therefore, considering in this case for the TVCT, all the pyramids with the same incidence angle with the Fluke approach is proper.
Okay, thanks, Giuseppe. So
you're welcome.
The next presentation is Raul Diaz Garcia, and is going to give a talk on a new metric for RFI impact assessment for small brightness temperature measurements. Raul, go ahead.
Yes, many thanks. I guess you see my screen now. I am Raul Diaz Garcia on behalf of the SMOS Calibration and Expertise Center based at ISAC, Spain. I'm going to present a new metric for radio frequency interference impact assessment at SMOS images. You are already familiar with the impact that radio frequency interference have in SMOS images, so I will not enter a lot of detail on this. Just to say that they are man-made emissions on passive measurement bands, and they affect quite a lot SMOS data, essentially by preventing level 2 retrievals, but also, which is a more insidious effect, by biasing the measurements. Although a lot of effort is going into tackling this issue by forcing proper regulation enforcement, and also on the filtering domain, so filtering post-processor or in instrument level, we will have to coexist, unfortunately, with the thing. Historically, we look at RFI by looking at them like this at the snapshot level. A snapshot is basically an ensemble of pixels taken by a single acquisition process of SMOS. And here, for example, you see some RFI that appear as high energy concentration, and also with some artifacts that come from the reconstruction process. But actually, SMOS, it doesn't use this directly to retrieve level 2 geophysical parameters, because SMOS is a multi-incidence angle instrument. And for each pixel, actually, what we have is a collection of measurements done for different incidence angles. And this is what the level 2 processors take advantage of to retrieve soil moisture and ocean salinity. So we should rather, instead of looking to the RFI like this, we should be looking to how the RFI distort the incidence angle profile. So this is what is really used. Our metric proposes to look at RFI directly to in this domain, and by quantifying the amount of distortion in this domain, we can also look back and consider the spatial impact of the RFI. So the big question is how to quantify and evaluate distortion at that level. Our basic idea is based on the basic comparison of the data that we want to test for RFI with an appropriate model. It's important to raise the thing that we prefer not to compare directly the raw data, but to compute at a constrained polynomial best fit of the data, because this reduces the impact, for example, of radiometric error into the comparison. Of course, the difficult question is what to use as our model for the data. We could, for example, use the incidence angle forward model for taking into consideration the properties of the surface, we can derive a forward model and try to apply this to the data. But this would introduce a lot of dependence on ancillary data. So we prefer to use first to test it with empirical models computed directly from the data, which is a bit tricky because we have to guarantee that the model and the data are compatible. They are basically under the same geophysical conditions than the data, but without the RFI. And this is, of course, not general. But it's enough to take some RFI under known areas and under certain conditions to test this metric. When we have a clear mind of what we want to compare, then the comparison itself can be quantized by, for example, computing the mean square error between the model and data, and also the Pearson correlation coefficient to have a hint on the shape distortion of the signal. And the results can be, of course, plotted for area assessment. The first test site that we have considered is an interesting RFI that appeared on Antarctica, just for one single product in BPOL. It appeared on the 15th of January 2020. And it's a very interesting issue because this appears in a very stable environment. Antarctica is the best environment possible, so we can very securely use this empirical model that we propose. This is the model in the left and the data which could be affected by the RFI in the right. This is for a pixel far away from the RFI source, so we don't expect a lot of distortion here. And actually, you can see how the product follows quite well the model. So we can conclude that no distortion is present here. But when we move closer to the RFI source, this is the kind of distortion that we could expect in the polynomial. So it's not the important thing is not the data itself, but the fitting polynomial. And as you can see, essentially gets totally distorted with respect to the model. If we quantify the amount of distortion with the mean square error, it's we prefer to look at square error by splitting the low incidence angle impact and the high incidence angle impact, because as you can see here, the impact is severe for high incidence angles, but practically non-existent for low incidence angles. This is an interesting result, which was expected because of the. This is coming because of the directivity pattern of the RFI sources. As the RFI sources point usually towards the horizon, it appears to us as the satellite has high incidence impact. This also means that we could be in the low incidence part without much impact. Looking to the distortion on the correlation coefficient, so basically the impact on the shape, being this low power RFI, no much impact is observed. We basically go from 1, which is the ideal correlation coefficient, to up to 0.9. The second site that we have considered is a stronger RFI, which was on for 4 months, since November 2015 until February 2016. It was located in an arid area around Kerrville Municipal Airport. The good thing is that this RFI is on for a long period of time, so we can assess the long-standing impact of this kind of RFIs. And this area is sufficiently stable only for winter, but we have constrained analysis in winter. Of course, if the RFI is always on, the question is how we can select data that is not affected by it. So to overcome this, what we use is data from the same period of the year, so in January, but just 1 year before. We hope that this would be enough to first idea of how the distortion affects data. And effectively, here I present a non-affected RFI, so a PGG point which is far away from the RFI source. And as you can see, both model and data are pretty comparable. When we move closer to the RFI, and please note that this is a strong RFI, of course, the polynomial fits get completely and utterly distorted. Looking quantitatively to the data, the mean square error is able to extract the RFI information, so it shows the RFI, and this was to demonstrate that this metric works. This is for ascending orbits, and this is the same data for only descending orbits. And this is an interesting result that we got also, that it seems that the orbital direction influences the RFI impact. This could also be originated by the differential directivity patterns that the RFI may have. Probably is not omnidirectional. So the RFI, this is the same, but for low incidence angles, and as you can see, the impact is much less. So the same conditions that I said for the Antarctic RFI are valid. The RFI should affect us more in high incidence angles than in low incidence angles. In this case, the distortion of the shape, as it can be seen in the example that I showed before, it's much severe, especially for H-pole, and this, we think it's a general result. Probably most of RFI affect more H-pole than B-pole in terms of distortion of the shape, because it completely distorts the natural behavior. H-pole for phase goes downwards with incidence angles, and the RFI affecting high incidence angles makes the shape completely change its direction. So as a summary, we want to raise the issue that RFI impact physical retrieval by distorting the incidence angle profile, and so we should look at this domain for a more accurate description of what's happening and how RFI are affecting us. So we have defined and proposed new metrics for aggregate assessment, and we have studied a couple of cases to see how RFI impact us most. We want to, and we plan to use this metric to study more cases, especially for high power RFI, where we observe some artifacts in the image reconstruction at the snapshot level. We want to understand how this translates to the angular domain, and if details appear there or not. And just the last point, that we also use this technique we are using this technique currently to validate SMOS following processor, which is SMOS level 1 OP version 750, which contains a filtering algorithm for RFI. And here just I want to show an example of this. In the left, I show the Antarctic RFI with the current operational version of the level 1 OP 620 version without RFI filtering. And in the right, I present the same data, the same conditions, but with a newer processor and with the RFI filtering on. As you can see, this metric is able to also to show how the improvement on the RFI impact brings the new processor. That's all. Thank you for your attention. Do you have any questions?
Thanks, Raul. Any question for Raul? I have just one curiosity. You show that in the Antarctic case, the RFI is emitting at quite high grazing angles. So since we have measured a lot on in Antarctica, we carried out a lot of measurements.
Yes.
What about this possible scenario? I mean, an RFI source located inside of a building, with a metallic building, with the waves that are coming out through a window. Could it be possible or not?
It could be. It could be. As long, well, this RFI has very low power, so this could be the origin.
Yes, a very low power, but with the waves coming out through the window.
Probably, yeah, we could see. It depends very much on the observation geometry. Which depends on the satellite path and the direction of the window, etc. But yeah, we should observe it as a RFI pointing to the horizon. Yes, as a high incidence angle incident.
Okay, thanks. Some comments, questions for Raul? Maybe from YouTube? Not. So thanks, Raul. And right now, the lead of the session is going to take over by my colleague Ada. Ada, you have the
Thanks,
floor.
Marco. I'm here. So
Go
we,
ahead.
we changed the guard. So the next speaker is Marie-Laure Fréry. Marie-Laure, there?
Yes, so I'm here.
Okay, we are waiting. That's
Yes,
good. You can start.
I think it was a wrong screen.
Yeah,
No?
no. It disappeared. Try again.
It's not the.
Yeah, I see. We see the presentation.
You see the presentation? Okay.
Yeah, yeah. Put it in presentation in show mode. Okay.
No.
Okay.
The presenter mode or the full screen mode?
No, in presenter mode. Yes, this is full screen.
Okay,
That's
great.
right. You can go on, please.
Thank you.
You're welcome.
Thank you. First, I would like to thank you, the organizers, for allowing me to present this work. I'm Marie-Laure Fréry from CLS, and I'm working for the Mission Performance Center at the monitoring and of the Sentinel-3 MicroRad radiometer data to ensure quality and performances of the mission. And I would like to acknowledge my co-author on this study. So as it was already presented sooner this afternoon by Catherine Prigent, Sentinel-3 is one of the Copernicus mission. And it is a multi-instrument mission dedicated to provide high-quality data. It is composed of several instruments. Some of them are optical instruments, and the others are forming what we call the topography missions, coupling a SAR altimeter instrument with a MicroRad radiometer, and also the Doris instruments for the orbitography. So the MicroRad radiometer is combined to the radar altimeter to correct the altimeter range of the excess path delay resulting from the presence of water vapor in the atmosphere. In that goal, the MicroRad radiometer embarks two-channel radiometer, providing measurements at 23.8 gigahertz and 36.5. And of course, as a topography mission over ocean, the goal of Sentinel-3 is to provide high-quality estimation of the sea level. And we have strong requirements on the budget error on this estimation. And up to now, the main contribution in this error budget for the estimation of the global mean sea level is still the wet tropospheric correction. That is another name for the path delay due to the water vapor in the atmosphere. So we need to have a very good estimation of this parameter. First, I will present the context. So Sentinel-3 orbit is such that it flies over the Krems radar facility in the Kwajalein Atoll in the Pacific Ocean. You can see the position of this facility on the map on the lower left. And to avoid any interference and damage to the instruments, the MWR is switched to a specific mode at a given distance before and after the radar facility. And at the beginning of the mission, the MWR was switched 50 kilometers before and after the facility. But unfortunately, the 24th November 2018, an interference with a 36 GHz channel was detected on the brightness temperatures. The left panel, brightness temperature for the 36 GHz channel for different cycle in the Persian of latitude around the Kwajalein Atoll. And you can see that from previous cycles, the brightness temperature was consistent with geophysical signals. However, for the cycle 38, you can see this, this signal clearly not geophysical, with high frequency oscillations at the approach of the facility, and a peak value higher than 320 Kelvin. And you can remark also that the peak value has a Gaussian shape consistent with a radar interference. Now, if we look at the instrument's calibration parameter to monitor its health, we can see that the calibration parameters for the 36 gigahertz channel were impacted by the interference, while for the other channel 23, it was not. The level, the gain of the receiver gain has changed before and after the interference. And you can also remark, looking at the long-term monitoring of this parameter, that the receiver gain did not get back to its initial state. The analysis carried out did not highlight any impact on the brightness temperatures, confirming that the instrument is still correctly calibrated with the in-flight 2-point calibrations. But the instrument has been stressed by this interference, and fortunately, there is no impact on data quality. However, the instrument could not suffer too many of these interferences before suffering irremediable damage. Consequently, actions were taken to protect the instrument, consisting first in the enlargement of the safing zone. This event was the first of its kind on Sentinel-3 data, as confirmed by this plot here. You can see daily statistics of the brightness temperatures for both instruments, Sentinel-3A and Sentinel-3B. You can see here average, standard deviation, and minimum and maximum value for each day for both instruments and both channels of both instruments. And you can see that on the maximum values, only one occurrence of interference can be is noticeable for the channel 36 of Sentinel-3A. But this event was of exceptional amplitude, but we can wonder if there has been other interferences of smaller amplitude. If there have been some, these events would not be as dangerous for the instrument, but they could degrade data quality by adding an additional signal to the geophysical one. So first, let's get back to the event of the 24th November and look at the signal. Here we can see that there is a high frequency signal just before the peak value, and that the signal is not a natural one. Now, if we look at the spectrum signature, here I first show the case of a pass. A pass is a Alpha orbit from pole to pole. This is the spectrum of the brightness temperatures for the two channels of Sentinel-3A for a pass where there is no impact of an interference. You can see that on a normal situation, you can see that the spectrum is a flat for all the scales lower than the MicroRad radiometer resolution, a different one for each channel, and a decrease of energy for the scales between 1000 and the resolution of the microradiometer pixel. The noise plateau represents here the MicroRad radiometer noise, also called the sensitivity of the MicroRad radiometer. But looking at the particular case of the 24th of November, we can see that for the 36 GHz channel, we observe a slope in the noise plateau where we were expecting a flat plateau. We observe this noise, highlighting additional energy in these scales, where only the noise of the instruments were respected. Over Alphen orbits, the computation of the spectrum is performed by splitting the data in segments. So we can look at each segment separately. And to have the average segment, to have the average spectra, we average all the spectra from individual segments. And we can look at the envelope defined by all the spectra and the percentile statistics. The average here is shown with the black bold lines and the median value with the red lines. For the 23 GHz channel, we can see that all the segments are flat in the 20 to 5 kilometer scales, while the 36 GHz channel, you can retrieve slopes in these scales. Also, we can see that the medium spectra is flat, while the average one is not, meaning that there is some very energetic segments. So using this technique and this specificity of this interference, we can wonder if we can be able to detect other RFI with smaller amplitude than the event of the 24th November of 2018. And if you can be able to locate the segments impacted by the RFI. So you use the slope of the spectrum between 5 to 20 kilometers for the cycle, for the 36 GHz channel, processing all the data available, and we're able to detect 23 other RFI for this particular channel. Here you have the cycles and number of pass of these detections. That means that apart from the exceptional event we had in 2018, there were other interferences. And if at the location of these interferences, we can see that they are all located around the Krems area, and that they can be interferences quite far from the Krems area. You can see here at the center of the circles, it is the Krems radar facility, and each circle represents the first one 50 kilometers, the second one 100 kilometers radius, and the big one in blue 300 kilometers radius. So you can see that all numbers of passes cycled in red were impacted by the radar facility, which represents a large area in the ocean. Now, if we look more closely at the case of the cycle 38, you can see here some outputs, the detection tool. The graph on the left represents all the unitary spectra computed for all the segments along the half orbits. Of course, the unitary spectra are noisy when they are taken one by one, but we are looking at for some very specific cases here. And you can remark the purple spectra here with a very high slope in the lower scales. The middle graph provides the allocation by using the same color. And on the right, you have a graph using showing the brightness temperature of the 36 GHz channel using the same color for each segment. You clearly see here in black the radar interference with a very high value. This segment was not processed during by the tool because it was cut. It was not complete, so it was not processed. That explains the gap on the map also. But you can see that before and after, the segments with very there were segments that were impacted. Another example here for that occurred sooner in the cycle 34. Here it is maybe
Marie-Laure,
difficult.
Excuse me to
Yes?
interrupt you. You have 2 minutes left. Sorry. Please go.
So I will try to go quickly.
Okay.
Another example here. It's more difficult here, but this this cycle has another characteristic is that it occurred during the tandem phase between Sentinel-3A and Sentinel-3B, during which Sentinel-3B were flying 30 seconds before Sentinel-3A. So they were very close on the same orbit, and so we can assume that they have seen the same atmosphere. Here you can see on the left a map of the residuals between Sentinel-3A and Sentinel-3B after co-registration. You can see very small differences between the two instruments, apart from two small you can see in the middle of the Pacific Ocean. And looking at the profile of the brightness temperature for the 36 GHz channel for Sentinel-3A and Sentinel-3B, we can clearly see that Sentinel-3A were impacted by the interference, but not Sentinel-3B for this pass. So it's one of the two paths you can see on the residual. But if we look at the second one, regarding another alpha orbit, again, this example was not detected by the tool. Amplitude is lower, but it can still degrade. The tool was also used to process Sentinel-3B data, and no interference were detected for Sentinel-3B. In the cases that shown slope higher here were due to incomplete. And so in conclusion, so Sentinel-3 has known interference of exceptional amplitude, which change is its operating point. We developed a method of detection of interferences with a smaller amplitude, and we detect 23 other cases of interferences that, of course, will not damage the instrument but degrade quality. Some of them occur during the tandem phase that allowed to confirm the interference and estimates the amplitude of the additional signal, but also show that some are not detected, and we have still work to do to detect those particular small amplitude interference. And finally, impacted data in the product to inform users of the degraded quality of the wet tropospheric correction in this segment with interference. And that's all for me. Thank you for your attention.
Thank you, Marie-Laure. Is there any question from the audience? A quick one, because we are a little bit late.
Yeah, sorry.
You're welcome. If not, I'm sorry, Marie-Laure, I have to keep the time, and
yes,
maybe
sure.
other question, or by the chat, or our colleague may ask you question. Thank you so much. Sure. The next speaker is John Bradburn. John, are you there?
Yes, I am. I am going to click share.
Okay, you can share. Okay.
Yes. All right. I believe it should be visible now.
Seen. Perfect.
Okay.
You can go on.
All right. Bye. Thank you. So my name is John Bradburn. I'm a graduate student at the University of Albany in New York. My two co-authors here, Mustafa Aksoy is my advisor, and Paul Rissett is our collaborator from Goddard Space Flight Center at NASA. So this work was funded in part by a NASA grant. And the name of my presentation is Microwave Radiometer Gain Characterization via Ensemble Analysis. So I was going to briefly skip over this. I'm just going to discuss this motivational background, theory, and the newer part of the work is a sample study on some actual radiometer data, whereas most of the work we have presented so far has been on simulated data. So, analysis of specifically non-stationary radiometer gain is challenging, and we typically consider gain to be linear, but this analysis is usually challenging as it cannot be independently monitored, and different calibration schemes can display different characteristics. So we are trying to provide a framework to characterize gain as a Gaussian or a non-stationary process. And in this presentation, this is characterizing it as an AR1 process, which is weakly or wide-sense stationary. And this should be able to be used to evaluate calibration error and uncertainty due to temporal variations. So move on. So what we have here, I think it is showing the full screen view, right? Okay, because it shows orange around the whole thing. I was kind of confused for a second. My bad. So I said this is a technique that you want to use to characterize stationary and wide-sense stationary gain. So what we are aiming to do is to characterize it as an AR1 or an equivalent process, which represents this radiometer gain under a specific calibration scheme. So in this figure, we show that what we have is a ensemble set of voltages for the random process, which will define the radiometer gain. So basically, from these time series, we want to accumulate a set of gain samples to essentially form a kind of a, how do I say, use sort of a Monte Carlo method to estimate the uncertainty using a number of gain samples. And I think that I had this on a following slide as well, so I'm going to continue. So this is based on two models that we developed. One is a analytical model of the uncertainty, and another is this numerical, I suppose, model of uncertainty, which we kind of created. And so in one here is we define the uncertainty of the estimated antenna temperature. And we arrive at this equation 3 by performing a multivariate Taylor series expansion about the mean value of each random variable in this equation 1. And this equation 3 is what I will is the analytical model that we are using in this presentation. And I'm sorry, I'm sort of I suppose flustered, but I am I'm sorry if I ramble or go too quickly at certain points. So so this is something I wanted to show. So the AR process is defined here, and the it is essentially a lag term and with a Gaussian noise as well. So we have two parameters that we are basically trying to solve for to characterize this process. One is this beta 1 parameter, which essentially describes the correlation between gain samples and is sort of a measure of the non-stationarity, if you will, of the process. So if beta 1 were to be 0, it would be a completely Gaussian process. It would be a Gaussian process. And for values of beta 1 of 1 or higher, it will be non-stationary, where weakly stationary processes will have a this value will between 0 and 1. And the second parameter, which we are characterizing, is this variance of the noise of this Gaussian process as part of the AR1 process. So here I've provided equation 3 again, but this figure shows, as I was saying before, this blue line is the analytically determined uncertainty. And here we are still using our simulated data, our simulated gain samples to create this red trace. And we essentially form a system of equations, which we solve graphically, and this will be shown in a few slides. But as we have so I'm just taking like a moment to catch up with myself. As we have we essentially need at least two values, obviously, to solve for two parameters. So here, this is a 3-point calibration, although the next one we are doing a 2-point. But I'm going to go on. Oh, and this is the weakly stationary or wide sense stationary case. So in a non-stationary case, this is we have not completely solved this. It is difficult to characterize a non-stationary signal. So this is also, as I said before, where we have a beta 1 here, and our simulation is 0.95. So this is essentially close to being completely non-stationary, but there is not a trivial analytical relationship that we have not found a trivial analytical relationship between the statistical properties of the radiometer gain and the antenna temperature for a non-stationary process. So we characterize it as an equivalent AR1 or Gaussian process. And then, as I was saying before, the third case is a Gaussian process. So if we assume that the measured pregain voltages are stationary Gaussian random processes, IID Gaussian random variables, that is, we can analytically solve this to characterize it as a Gaussian gain. So this is what we also have sort of done for a considering it as a non-stationary process. And in this case, we consider the variance of these voltages in equation 4 here. So the process that we have here essentially is that we have an we create an uncertainty, what we kind of call an uncertainty curve. These contour plots, we vary these two parameters. It's essentially a lookup table in these, where on the y-axis we have this beta 1 value, and on this x-axis we have our noise variance term. And what we do is we essentially solve the system of equations that I described before by the intersection of these uncertainty plots at a certain at the same contour line at one of.
I'm sorry to interrupt you. You have 2 minutes left.
Yeah, I was kind of glancing up at the time as well, so I will try to be quick. But we solve this graphically at the intersection of the contour at the uncertainty level obtained from 2 different points. So this at this first contour t equals 158, we pull from this point, and this t350 at this point, and the uncertainty level at these 2 points is found on each contour, and then at the cross section, or the point where those two cross, we that's where we determine the value of these two parameters. So as I said before, we we're using simulated data before. So more recently, we wanted to try to use this on data collected from the PALS radiometer in 2012. The results that we obtained did not exactly match up with our sort of analytical model from before, but there are, it essentially was not as clean. And I think there are several considerations that we need to make. The antenna measurement of the PALS radiometer is not constant over time. We did not really model these changes in the radiometer simulation that we had. Previous simulations, we assumed the gain signal was a Gaussian or AR1 process, and the underlying gain process of an actual radiometer is certainly nonlinear. Certainly more complex than we were modeling in our simulations before. Calibration may be too sensitive to long-term trends in the data, which is something that we also did not fully consider in the previous work. So, and also this will be find better performance for situations where there are simultaneous observations of the calibration and targets of the references and the antenna. Obviously, you cannot observe all of them at precisely the same time with the same receiver. So this is an assumption that we made and that we can make with simulated data, but does not really carry over to actual measurements. And I think I am running right up against the end of the time. I think this is my last slide. So we found the uncertainty to be somewhat higher than we expected using this method, but due to these sort of issues, kind of assumptions in the linearity of the process, there are things that we want to adjust for the future. So I think that is kind of my time. If you have any questions, here's our contact information. And I think that is all.
Okay, thank you, John. We are a little bit late. Maybe that people may ask you a question through chat, or unless there is a quick question to ask to John. If not, I would like to go on. Otherwise, we are already late. If there is no question, I will proceed to the third presenter, which is Alam Gir. Thank you, John, for your presentation.
Thank you.
Thank you. I'm sharing my screen.
Okay. We are waiting for your screen. Okay.
I believe you see my screen right now, right?
Not yet. It begins. Okay, that's good. You can go on.
Okay. Thank you. Good afternoon. This is Alamgir Hussain. I'm a PhD student at the University of Central Florida. So I will present 3 microwave emissive reflector correction result for version 7, GPM version 7 reprocessing. I would like to thank my advisor, Dr. Leonard Jones, for his guidance. Tropical Rainfall Measuring Mission TRIM was a joint mission by NASA and JAXA for precipitation measurement over the tropics. It was in non-sun synchronous orbit. So the figure on the top, you see the curtain of TRIM observatory showing different instruments, including TRIM, including TMI. So TMI was the passive radiometer. It was one of the measured instruments on board TRIM. And the figure on the bottom shows the sample 1-day coverage of TRIM. So as we see, this extends plus minus 40 latitude, which covers the tropics. So TMI was a conical scanning radiometer with around 850 kilometers SOAD. So the figure on the top shows the main reflector of the TMI. This is forward scanning. This is backward scanning. I believe my slides are moving correctly, right? You see the main reflector of TMI? Excuse me. Okay, I believe it is switching. Okay.
And we see your presentation.
Okay, thank you. All right, so it had 5 frequencies. All were dual polarized except 21, and it provided 17 years of very important data that was very crucial for understanding the hydrological cycle over the tropics. It also worked as a calibration standard before the launch of GMI on the GPM observatory. So the accurate calibration and stability of TMI data was very, very important. And my work here is to make sure that. So as a history, during post-launch calibration around 2000, it was discovered that TMI main reflector, this main reflector was a little bit emissive, so it add some extra emission to the brightness temperature. With added some bias. So TMI brightness temperature went through different correction, different versions, and each version included a different kind of correction, some ad hoc correction. With the latest one, which was very good, it was ready to transfer theory-based approach by Faisal El-Quaid. However, the current data, GPM version 5 or TMI version 8, still has some emissive signal. So we in this presentation, we worked to remove the emissive signal bias. So this is the current bias for 2 different EO 0, EO 180. The black is for EO 180 and blue is for EO 0. So this is the double difference with GMI using the current version 8 TB. So as you see, in all channel, especially for the low frequency channel, there is a obvious emissive signal. So this is related to the orbital phase, which is related to the day-night cycle of the main reflector or the observatory. So it should be flat, and our work is to make it independent of orbit phase. Okay, so what we did is we estimated the physical temperature because TMI did not have any physical temperature sensor. So we estimated the physical temperature and made the lookup table again using a modified and improved approach. And then using the new table, we derived new brightness temperature that will be included in the version 7 in coming year. And our new table seemed to remove the emissive signal present in version 8 in sufficient level. So these are the we use to derive the physical temperature or to estimate the physical temperature of the main reflector of TMI. This is the version 8 antenna pattern corrected brightness temperature. This is the on-orbit measurement. And this is the modulated simulated TB. We included a term or TM error, which is for the compensation in the radio transfer model, because the radio transfer model, whichever the model, it has some error. So we modified the simulated TB using this term. And these are the emissivity values that were derived from deep space maneuver of TRIM during 2015. So using this, we can derive physical temperature. And we showed the physical temperature in a 2-dimensional table based on beta, solar beta, and orbit phase. And the lookup table is used to derive new physical temperature. And finally, the new TB are compared to the GMI TB. So GMI is very accurate and stable and well calibrated. So that's why we compare to GMI and show the result here. So this is the shape of physical temperature. The x-axis is the orbital phase, and y is the physical temperature here at the top. For different channels, different color represent different channel. So 10 to 37 gigahertz, V and H, 6 different channels we used. The figure on the bottom shows the residual. So as we see from the residual, we see the pattern of physical temperature in all channels looks similar, but there is a small DC bias between the channel. So, and this is similar for EO 180, but a little bit different because EO 180 has some the solar geometry different from EO 0. So this is shown for all beta, averaged over all beta, and this is now over beta, all beta, and orbital phase, the 2-dimensional table for EO 0, EO 180. So this is the variation of physical temperature. You see the color bar. The physical temperature varies 210 Kelvin to 310 Kelvin, roughly. And this is the comparison with the new physical temperature with previously estimated physical temperature. We see a little bit different, and this is gradually increases with orbit phase. So we see that the difference. So in terms of brightness temperature, this is emissivity times the physical temperature. So emissivity is 3% of the physical temperature. Then it would be like here we see the 10 Kelvin difference. So it would be 0.3 Kelvin for this beta and orbital phase, but it could be different for other coordinates of the table. So this is for example. So hopefully it will remove the emissive signal present in version 8. Let's see the result. So we derived the new physical, we estimated physical temperature, made the lookup table, and derived the new TB that will be included in version 7 of GMI, GPM version 7. So this is how we validate our new TBs. We use the new TBs and GMI TBs and collocated them using radiative transfer model. We can produce the simulated TB correspondingly and use the Xscale double difference technique, which is illustrated here. That is actually the measurement of the measurement comparing with the model, and that result the single difference, and the difference between the single difference and the double difference, which removes the systematic bias between the model and the sensors. Okay, so this is the result for EO 0 using the final table. So the blue curve represent the version 8 double difference with GMI, and red curve represent new TB that is derived using new table. So as you see, all red curves looks flatter than the blue curve, so which represent the improvement of the new lookup table, new physical temperature table that we derived in all channels. So we see a significant improvement. Then the double difference, the bias between TMI and GMI is independent of orbit phase or any or there is no any day-night cycle in the bias. So we should be the usual case. So this is the same result. We are just showing for 2 different beta because the bias is function of solar beta and orbit phase. So 3 different beta range, 20, 40.
Arangis, sorry, you have 2 minutes left. Sorry to interrupt you.
No problem. I've already finished. Okay, so this is 3 different beta range. So what we are showing here is so the result is good for all beta range, and so hopefully we believe the new TB will be free from any emissive signal bias. So what we did in this work is we derived the physical temperature. We used different environmental parameter and radiative transfer model to make sure the new table would be free from any emissive signal, and we compared the new TB with GMI TBs. To validate the result that new TB will not have any emissive signal in it. Thank you for, and if you have any question, I welcome.
Thank you. Is there any question from the audience? No. Again, as before, since we are late, I suggest to ask your questions to Alan Gear through chat, unless from YouTube there is a question. And I will go to the last speaker, which is Mark Andrews. Thanks, Alan Gear, for your speech.
Thank you. Thank you very much.
Okay, can everybody see my screen and hear me?
Yes, it's correct. You can go on.
Okay, great. Thank you. So my name is Mark Andrews. I'm from Ohio State University's Electroscience Lab, and I'm presenting the UHF and L-band RFI environments in the polar regions using observations from UWB-RAD. So if you've probably seen UWB-RAD mentioned in several talks already, it's an ultra-wideband self-refined radiometer. It was developed under NASA's 2013 IIP program. And it's an airborne radiometer, and it measures from 500 to 2,000 megahertz and 12 separate channels. The antenna is circularly polarized, so there's only one polarization available to us. It's directed to nadir, so there wasn't a reason to have two polarizations when we made it. And it's been flown in 3 missions since it was created, 2 of them in Greenland in September 2016 and September 2017, and 1 in Antarctica in November, December of 2018. The vast majority of our bandwidth is in unprotected spectrum, so we get to see all kinds of RFI. And this presentation covers our algorithm approach, the thresholds that we use for our algorithms, and what the RFI environment using those algorithms look like. So first, a description of the data that UWB-RAD collects. We have 12 separate channels. It acquires 100 milliseconds of data at a time at 250 megasamples per second. We calculate kurtosis of the full band of all those samples, and we also take FFTs to get a 512-point power spectrum. So each 100 millisecond acquisition gets a 100 by 512 brightness spectrogram, with each pixel has a time bandwidth product of 1 millisecond by 244 kilohertz. We have 4 different algorithms. There's full band kurtosis, subband kurtosis, pulse planking, and cross frequency. And they are applied in that order, which I'll talk about a little as we go along. So the first one, the full band kurtosis algorithm. So of the raw samples that are collected, the kurtosis of each 1 millisecond window of that is calculated. Since this is the first algorithm applied and it flags the entire bandwidth, we deliberately set the false alarm rate to being near 0, a pretty wide threshold, so that we don't over-flag data that can be more precisely flagged by subsequent algorithms. Using liquid nitrogen testing and observing a thermal load, we determined that a threshold of 0.06 gave the false alarm rate near 0, but still allowed the majority of the data to be flagged that doesn't appear to be thermal. We also had an if statement in this algorithm, so that if we have a persistent RFI, for example, a CW tone that's present in the channel, if over 80% of the data is flagged by the full band kurtosis algorithm, it doesn't flag any of the data, and it all goes on and moves to the subsequent algorithms. After that is subband kurtosis. So within each 1 millisecond window, we take the FFTs, and you get a certain number of spectrum points, and calculate the kurtosis of those spectrum points. So after the full band kurtosis, we decided that a maximum overall false alarm rate of 7.5% would be good. So the goal of the mission was a 1 Kelvin NEDT. So assuming we were at 1 Kelvin, if you flag 7.5% of the data, you get 1.04 Kelvin, which using significant figures would still round down to 1. So that's why we did that. And we just allocated 2.5% to the remaining 3 algorithms to try to achieve this overall false alarm rate. Turns out with the smaller bandwidth and the smaller number of samples, you actually get very close to the same threshold for the subband kurtosis as we get for the full band kurtosis of 0.057. After that, now that the non-Gaussian behavior seems to have been removed, we try to identify any remaining outliers in time and frequency. And in time, we use a pulse planking algorithm, and in frequency, we use cross frequency. Both of these are based on the median absolute deviation method described in PEC, which the reference is at the end of the presentation. Essentially, you take the median, you subtract the median value of each frequency bin over time, then take the median of this deviation, and that gives you what's called the median absolute deviation, delta. And anything that exceeds 4 deltas from the median value is considered an outlier and is discarded, or 4.01 for the pulse blinking. In cross frequency, the same thing. One thing to note, being a wideband radiometer, there are natural gain and power differences across frequency. And if you don't want to flag a peak or a valley and across frequency, you have to somehow flatten the spectrum. So to do this, we did a moving 1 minute filter over time to kind of flatten the frequency response, and then performed the same MAD method, which with a threshold of 3.5 instead of 4.01. So to get a baseline of what things would look like, we looked at the liquid nitrogen test for UWB-RAD. Instead of presenting results at 244 kilohertz, we use 10 megahertz because it's easier to read and it's more of a convenient thing for people to relate to. These are the results for liquid nitrogen testing. So this is a CCDF. To read it along the y-axis, at least that percent of the spectrum was flagged, and the color represents the percentage of time. So for example, if you come across 20% here, it's kind of green. So at each frequency, 20% of the spectrum was flagged about 1% of the time is the way to read these charts. And you can see there it was largely pretty low. There's a few, minor spikes. These results near band edges can be taken with a grain of salt. Sometimes there's not much data there, and it's kind of a statistical anomaly that results in that being there. And the frequency drifts over time, which is why there's not as much data in certain bands. So finally, getting to the actual RFI environment. So in Greenland and Canada, definitely at lower frequencies, there were higher amounts of RFI, but no portion of the spectrum was completely unusable. We were always able to get data at every part of the spectrum. We split it up in between transit flights between Canada and Greenland to show kind of the results over anthropogenic sources and in the presumably quieter environment of Greenland. Other than, so I mentioned below 1 gigahertz, it was more flagged. Between 1 and 2, it was still pretty viable. So within Greenland, you can see these yellow spikes at the lower frequencies indicate higher portions of RFI. This bit here is, we believe we've traced that to using the satellite phone in the airplane. The full band kurtosis algorithm would get triggered and flag much of this channel. And there was always, even in the liquid nitrogen testing, there was always some internally generated RFI around here. But for the most part, it was pretty clean in Greenland. And the transit flights between Canada and Greenland is much worse across the board. Probably saturation or out of band interference because it's uniform across all frequencies. But identifying exact sources of RFI can be a bit of a challenge. In Antarctica, we also, other than the flights that we performed, we also did a sky calibration test on the ground performed at Marty Zakeli Station. Overall, showed less interference in Greenland. And the ground test was important because the in-flight results show a good deal more RFI than the ground results, suggesting that probably the aircraft is emitting something that is impacting our measurements. So here's the sky calibration test. You can see, all these blue spikes are pretty low percentages, and there's a little bit here. But for the most part, it was a very clean RFI environment in Antarctica. And when you move into the aircraft, especially at these lower frequencies, you get a lot more spikes. So that's why we believe that it's being caused by the aircraft. So I kind of already mentioned the discussion here. Looks like it's caused by the aircraft. Some source of RFI, the satellite phone and the airplane was consistent with the Iridium telephone frequencies. And looking at our notes from the flight, it appeared that that was in fact what was causing the RFI. Just a note here, if anybody saw a minor spike around close to the protected band here, it actually turned out that was an internal interference that we found. We changed the thermal set point between the Greenland and Antarctica campaigns and resulted in there being some internal interference right at the protected band. So my conclusions, definitely radiometry from 500 to 2000 is still possible, and RFI mitigation is an absolute necessity. But even if you're operating in protected bands, you probably still need it. We flew on a Basler in Greenland and a Twin Otter in Antarctica. In both cases, it appears that it probably contributes to the measured RFI. So ground or space-based radiometers may experience less interference. Canada was much worse than Greenland, not too surprising. And we believe that out-of-band interference might still be problematic. But if radiometers are slightly overachieving in NEDT, wideband radiometry should be good everywhere. Thank you.
Okay, thanks. Thanks, Mark. Is there any question from the audience?
Al Gashevsky, I've got a question, Mark.
Yeah.
How did you set
please go.
How did you set the power into your A to D converter? How many bits of padding did you use to account for RFI versus thermal noise?
Yeah, so we did a test where we essentially just increased the power going into the A to Ds until we could see a clear, get the signal while it's still linear. And then basically made it the minimum that it possibly could be to get clean radiometry data. And then that would go into the, so that way it gave as much dynamic range as we could for RFI.
Got it. Yeah. How many bits was that though for clean radiometry data, would you say?
Let's see, probably, I think the effective number of bits for the A to D was 12, and I think we probably got about 10.
Yeah. Okay. Thank you very much.
Yep.
Nice work.
Okay.
Thank you.
Are there any other questions? I have a curiosity, Mark. You talk about a process to remove the RFI through 4 levels. The first level, in the first level, you have the first alarm rate almost equals 0. In the second, then you have you put 20.5% just to not have a bad reduction. In the third case, the pulse blanking technique, you put coefficient 3.5 and then there is in delta CF. How did you choose them? Through heuristics or?
Yeah, so that was empirically derived from the liquid nitrogen testing. So we would get all the M8, the median absolute deviation, the MAD values for the liquid nitrogen test, and then just find out at which point was 97.5% of the data come through and which point was 2.5% of the data would be flagged. Okay. So, and it turned out for the pulse blanking, it was 4, and the cross frequency was 3.5. The cross frequency showed more variation over frequency. And that's a result of a couple different things that I didn't have the chance to get into because of the time. But yeah, basically, the cross frequency was a little more sensitive than the pulse blanking.
Okay, so the idea is that this is let's say a procedure, but maybe that in other situation, under condition or transit, you have to change or to tune your coefficient, or you will be.
Yeah, it could. So there's an argument for tuning the coefficients. I think for our perspective, we thought if it doesn't appear like thermal noise does, it's go ahead and safe to eliminate it. And a lot of that was just opportunistic collection anyway, like over Canada, that was just collecting because we had the opportunity. It was not part of our mission at all. But yeah, in Greenland, we wanted to try to get rid of as much RFI as we could, and keep it. If it doesn't appear like the thermal load does, assume it's RFI. So.
Okay, thanks. Is there any other question? No. If not, I think that we are near the break, half an hour break, and to start again at 5 p.m. with the last session. Marco, do you have some advice, something to say to people?
No, just to say that we are going to reconvene here in half an hour. As Ada say, 5 p.m. Central European Time, 11 Eastern European Time.
Okay. So see you in half an hour. Thanks to all for participating. Bye.
Ada, sorry, there is a very last minute question on the chat.
Okay.
Maybe we are still in time to ask.
This for Mark, yes.
Yeah, I can hang out and still talk about things.
You can answer in chat.
Yeah, everybody else is welcome to take their break. Regarding Giuseppe's question about the bits reserved for RFI, so our analog to digital converter was a 16-bit analog to digital converter, but it has an effective number of bits of 12. So when we were setting it, I didn't reserve it. I didn't set the gain in terms of bits, so I don't know the exact answer. I'm estimating, but I believe that probably about 9 to 10 of those bits were reserved for RFI, I would say. It was, I believe we set the input power as around minus 50 dBm, and the peak-to-peak voltage of it was 1 1/4. Well, or no, it's 2.5 volts peak to peak, so one plus and minus 1.25. So if anybody can do that math, figure out the actual number of bits, then you'll know where about we're at.
Thank you, Mark. Thanks a lot.
Yep. Okay. See you later, guys.
See you later. Bye.
Okay. It's beginning the break. Only very few minutes for people who will be the presenter in next sessions. In the list, we have George Brost. Can you hear me, George?
Yes, I can hear you.
Hi, George. I make you presenter.
Okay, here
Okay, now
I'll...
you are presenter, and you could be able to share your presentation.
Yes, do you see it?
Yes.
Okay, thank you.
Okay, perfect. Thank you very much.
How do I unshare?
No problem.
Okay, I see okay, thank you.
Okay. Another is Giovanni De Amici. Can you hear me? I see you on
Ti sento.
Okay. I make you presenter. Okay, now you should be able to share.
Should, but don't.
Should, but don't. One moment. Okay, you can repeat again. No. You lost the connection. Okay. We have Edward Kim.
Yes, can you hear me?
Hi, Edward.
Yes.
You lost the connection. Okay.
And I can try to share screen.
We have Edward Kim. Yes, can you hear me? Hi, Edward. Yes. You lost the connection. Okay.
Try to share.
We have Edward Kim. Yes, can you hear me? Hi, Edward. You lost the connection. Okay. Perfect. Okay. Could you try to put full screen? Okay, not important. Just...
Simone,
Sì? Dimmi.
mi senti?
Sì, ti sento forte e chiaro.
No, perché siccome Paolo dopo dirà due cose, volevo capire se l'audio era buono.
Ci si sente bene? Sì, sì.
Bene, grazie. Ciao, ciao.
Ciao, ciao. Okay. In the list there is Vincent Leslie.
Hello.
Hello.
Can you hear me?
Yes.
Great.
The microphone is good. now you can try. Yes, share. Okay, perfect.
Okay, full screen look good?
Full screen, perfect. Very well.
And this is Ed Kim again. I'd like to check my audio, please.
The audio, okay. Oh, sorry. We can try another with Giovanni D'Amici, who has a little problems with connection before. Okay, Giovanni, now you are able again to share.
Yeah, does this work?
Okay, now it's working. Okay, very well.
Okay, so if I do like this.
Very nice picture.
Okay, excellent. Thank you.
Thank you to you. Okay, we have Rachel Kreutzmann, if I pronounced correctly. If not,
yeah. Right, Rachel Kreutzmann, yes. Hi, can you hear me okay?
I hear you very well.
Okay, let me...
Now you are able to share.
All right. Okay.
Perfect.
You see my, all right, I'm gonna attempt the presentation because I have two screens here. So you probably see, do you see the presentation view?
Yes, this is presentation view.
So I switch and that's good?
Now it's full screen. There is a little rectangle on the right,
Oh,
but
it's
the Cisco. Okay, now it's left.
Great. Okay, thank you. I will stop sharing. Okay.
Okay, he remains Merck Andrews, but I don't see in online. Is where Merck Andrews? Okay, so now not. We'll try later. Okay, we'll see you later. Have a nice break.
Thank you.
Can other people hear me okay? This is Ed.
Yes, I can hear you.
Yes, we can hear you, Edward.
Thank you.
Thank you to you.
Rachel, are you there?
Hi, talking to me?
Hi.
Hi.
Yes, I sent you and Ian an email asking for the update on the next MicroRad. But I didn't get any reply.
Oh, I do have the slide. Ian had put together a slide. So I did, if he's not able to share, I could always share it on my screen. I believe he was the one that was going to, I don't know, I didn't see an email back from him. He might not have.
Okay, so we simply give you the floor and authorize the screen sharing, and you can proceed at the end of the goodbye. Okay.
Okay, yeah. Is it yeah, I guess what time will we be sharing?
Yeah, okay. We will reserve you the time, and I will introduce you for the announcement of the next MicroRad. Okay, good.
Okay, sounds great. Thanks.
Okay, it's 5 o'clock. First time to resume with the second part of the sensor calibration, RFI, and the spectrum management session. This is the last session of MicroRad 2020. So let me renew for the last time my annoying recommendation. Please keep the schedule. 10 minutes for presentation and 5 minutes for question and answer. Participants are allowed to pose to ask a question to the presenters directly by enabling their microphones or via chat, the two chat on WebEx and YouTube. And remember that after this session at 6:30 p.m. we will have the farewell and with the final comments and goodbye and thanks. And that's all. I will give now the floor to the session chair, Andreas and Ed.
Yeah, hello everybody. This is Ed Kim from NASA Goddard Space Flight Center. I'll apologize, my computer does not have a camera. You'll just have to listen to my voice. And I will oversee the first 3 papers in our session, and then I'll turn it over to my co-chair Andreas for the second 3 papers. We have our first paper from George Brost. And if George, if you can go ahead and share your screen, I'll give you a 2-minute warning.
Okay, thank you. So this paper is on tipping curve calibration, and particularly, how do we know how good it is?
I'm sorry, George. We cannot see your screen.
Okay. I thought, just a moment. Can you see it now?
Okay, now it's working. Thank you. Thank you very much.
Thank you. As I said, we're looking at tipping curve calibration. In particularly, what we're considering is 2-point calibration of a ground-based radiometer, where the cold temperature is determined by tipping curve estimate of the zenith brightness temperature. Recall that the basis of tipping curve is that in a horizontally stratified atmosphere, opacity is proportional to the air mass. Calibrations, therefore, are taken in clear weather where that assumption may apply. Line is fit to the data. The calibration parameters are adjusted until the intercept is equal to 0. Then the zenith opacity is equal to the slope, and that's used to estimate the zenith brightness temperature, and that's the tipping curve calibration. How do you know how good that is? Well, the conventional way is that statistical analysis is used to assess the quality of the tipping curve, and certainly that's how my commercial radiometers do it. Okay, acceptance thresholds get established. What's a good threshold? I don't know. The literature offers a range of values, and the choices seem to be rather subjective. So that's, with that background, this study was to look at how does the quality really relate to the acceptance criteria. The analysis that we did was analytical. So the methodology was to define a stratified atmosphere from model reference atmospheres, add random perturbations to the water vapor to create a non-stratified atmosphere, and then simulate the radiometer measurements and tipping curve. Do this many, many times and look at the statistics. So if we think about the statistical analysis, which is conventionally applied, if it's a good measure of the tipping curve quality, then I would expect that the RMS error that we would measure would, pretty much match what the inherent uncertainty is just due to the standard deviation of the slope, which you get out of the regression analysis. And the result would look like the plot shown here, and then we'd be done. Here are typical results from that. These are plots of the RMS error as a function of the regression coefficient. Black line is the uncertainty we expect from the slope. So what we can see is that depending on how we apply the perturbation and its magnitude, we get different results. So although they may be, let's say, possible occurrences, we really don't know what the natural distribution is. So I can't give, like, this is what the result is, an exact result. But what we find is when we apply, perturbate the water vapor in the atmosphere, it certainly does not match the uncertainty that we would get from the slope, and it's always greater, pretty much. So why is that? Well, the likely answer is gradients. A net horizontal gradient in the opacity doesn't affect the regression coefficient, but it affects the slope, and if you affect the slope, then it is an error. And it takes only a fairly small gradient, the calibration errors that are significant. If it's a uniform gradient across the atmosphere, then two-sided calibrations, tipping curve calibrations, would eliminate that error. They average it out. But when we apply these random perturbations, the one-sided and two-sided results look pretty much the same. So if statistical analysis is not really a complete measure of the atmospheric stratification, what is? So that leads me to the idea of spectral consistency, which is not conventionally used in tipping curve calibrations. The only place I saw this was introduced by this paper by Kukler, and they defined it as the standard deviation of multiple channel measurements of the brightness temperature of a reference black body target. So in their calibration experiments, that was liquid nitrogen. And they did many, many calibrations. And so when they did tipping curve, they also did regression analysis criterion and what they called spectral consistency. So what they found when they did that was tipping curves that passed one criterion often did not pass the other. And they, at that time, had no explanation for that. So applying the methodology that we did, we simulated their experiment. And the plot on the left is a scatter plot of the spectral consistency or the standard deviation as a function of regression coefficient. And the kind of results we get match, or at least are consistent with their experimental observation, that the two different criteria do not really match each other as well as one might expect. The plot on the right is a plot of the absolute error as a function of the standard deviation. So that result is really independent of how we applied the perturbation. But what it shows is there's really a very well-defined linear relationship that exists. And so the standard deviation is a measure of the absolute error. It depends on the error depends on the frequency, and it increases roughly with the water vapor opacity. So the error is not equal to the standard deviation, but it's somewhat greater, and again depends on the frequency. So Kukler did their experiments with liquid nitrogen. If I had to use liquid nitrogen, I probably wouldn't bother with the tipping curve, but there are other ways that it could be implemented. And for example, a matched load. So the key requirement is that each channel sees the black body, which is at a temperature, somewhat different than the two calibration points, the ambient and the zenith temperature. And you really don't have to know it exactly. The plot here is an example of a two-channel, one at liquid nitrogen and the other the black body at 400 K. So the effect of changing what the black body temperature is affects what I'd say is the slope or the sensitivity of the spectral consistency. We did, calculations at different values of water vapor opacity, and what you find is that it's weakly. The slope is weakly dependent on the opacity, so it seems to be fairly robust indicator of the air.
2 minutes.
Okay, and so the calibration errors are fairly well correlated because each channel is seeing exactly the same atmosphere, and there's a well-defined relationship between them. So this actually allows the possibility of adapting the calibration constants or to improve a calibration tipping curve calibration that is not otherwise acceptable. All this plot is to note that all of the above calculations were done with the assumption that there are no errors in the system, and so at some point you're limited by practicality of including the resolution of the radiometer. So in summary then, I would say that we didn't really accomplish the goal of relating the regression coefficient to absolute error. Well, we can say that it's not a complete measure of the stratification. On the other hand, the use of spectral consistency seems to be a very robust measure of the calibration accuracy. And I'll end it there. Thank you.
Yeah, thank you, George. We have time for maybe a couple, one or two quick questions. If anybody has one, feel free to unmute yourself or put them in the chat, either the WebEx chat or the YouTube chat. I guess while we're waiting, I had one question, which is, there are a lot of ground-based radiometers that use the tipping calibration scheme. How can you say something about how you potentially, how they might be impacted? Sort of what magnitude?
Well, that was the goal, and because they all use something like regression coefficient, and I can't give a quantitative answer because again we did these random perturbations, but I don't know. I can't say how the natural variations are, but what I can say is that if you think it's a high regression coefficient, it means it's more likely, but it doesn't ensure that it's an accurate calibration. If all you're going by is regression coefficient.
Okay. I don't see.
I have a quick question. This is Nico Cimini.
Hi, Nico.
Hi. Okay. Hi, George. In your slide, you showed that one of your slides, you showed that one or two side tipping curve provided similar results.
Yes.
And I guess that's assuming a perfect aligned radiometer, right?
That's correct.
Okay.
In these calculations, all the sources of error were assumed to be eliminated.
Okay. While I think that two sides should perform better if there is a small tilt in the instrument. I guess
if there's a tilt, yeah. But these calculations just assume that all the errors had been for.
Okay. Thanks.
Okay, I think in order to keep with the time, we'll move ahead to the second paper. Thank you, George.
Okay.
Is Mark, do you want to go ahead and share your screen, please?
Yeah. Okay. Everybody see my screen and hear me?
Yes.
Okay, great. From Ohio State University's Electroscience Lab, and this presentation is impedance mismatch effects on the calibration of wideband radiometers. So if you were just on an hour ago, you heard me talking about UWB-RAD. It was developed under NASA's 2013 Instrument Incubator Program. It's an airborne radiometer that measures from 500 to 2,000 megahertz in 12 different channels. Covering such a large bandwidth, you can't really use well-matched components in impedance. So there are reflections and standing voltage waves all throughout the system, and the impact of these can be pretty significant and can't be ignored for UWB-RAD or for any future wide bandwidth radiometers. So we want to perform some simulations that demonstrate the impact these reflections can have and the importance of monitoring phase changes in the system, which can generally be ignored for narrowband radiometers. So to do so, we generated, using noise wave models, these can accurately represent some of the reflections that are how they impact things inside a radiometer. The model that we used starts with an antenna or source on the left. We have what we call the external network, SX, which is, for example, a cable connecting the antenna to the radiometer. An internal network, SY, so for a wideband radiometer, you probably want to have a filter defining your bandwidth, and then the radiometer off to the right. For these particular simulations, we set the excess radiometer voltage to 0. Basically, if it were an LNA, it would be a very low noise wave, and we just set it to 0 to simplify these simulations and the results. So we compared two different models. There's what's called the simple reflection model. This is more typical for a narrowband radiometer. If you have well-matched components and minimal reflections, you assume the maximum available power from the antenna would be kBT. The reflections can be considered a loss term between the antenna and the radiometer. So reflected signals are going to be terminated in the antenna terminated in the antenna, essentially, radiated. And the relative phase of the components aren't going to impact the calculations because of this, and only the magnitudes will really impact the calculation. For the multiple reflection model, we account for all higher order reflections. There are different thermal powers coming out of each port of the passive network based on what's known as the Bosma theorem. The contributions from each component are impacted by changes in either phase or amplitude, and we used Mason's rule to calculate the exact transfer function. So that can be pictured here. So the previous model, the noise wave, incoming and outgoing noise waves are represented by the nodes in that signal flow graph. In the simple reflection model, the power at the radiometer would be given by this equation. So you have a loss due to the reflection of the external network, the transmission, reflection and transmission of the internal network, and the reflection at the radiometer itself. With the multiple reflection model, you have the transmission, S21, in the numerator, and in the denominator, it's you subtract the first order loops gains, you add the second order loops, you subtract the third order, and you would keep on going if you have higher order loops. But for this particular model, that's the limit of it. But this is the transfer function. Then you have a normalized voltage source that changes with impedance, and the power is going to be this magnitude squared minus the reflection at the radiometer. So to illustrate it, we did a Monte Carlo simulation. We tried to keep things similar to what UWB-RAD saw in its polar campaigns. and that's referring to the temperatures of the antenna, the external network, and the internal network. We simulated 3 different magnitudes of the interfaces. So if you have 30 dB reflections at each component, if you have 20 dB, and if you have 10 dB return losses for each of the components. Here's a table giving more of the simulation parameters. We did 1,000,000 times. These are the temperatures we set for each thing. We did a half dB just as a value for the internal and external network transmission losses. And reflection magnitudes, as I said, we varied. During the simulation, after randomizing the phase, make sure that it's a realizable passive network. Reference Carly here. Standard ones that everybody knows, oh, that's a copy paste error, but basically making sure it's passive, going in both directions, reciprocal. And then this last criterion, make sure that the phases that are used for each simulation are also realizable. So for 30 dB reflections, you can see in this plot, the x-axis is the offset of the radiometer. So this is the contributions coming from the X and the Y networks. And then along the y-axis is the antenna to radiometer gain. So this is essentially the efficiency going from the antenna to the radiometer. This red dot is what happens with the simple reflection model. And the blue dots are what happens as you randomize the phases of each of these components. So you can see the change of each particular component to the overall input temperature at the bottom here. So the antenna can be plus or minus 1 Kelvin. And when you combine that with the changes to the offset, you get a total of about -2 to +3 Kelvin as your total input temperature to the radiometer. When you have 20 dB reflections, it gets quite a bit larger. You can have a change in your antenna temperature up to 7 degrees and plus or minus approximately 15 degrees for the total. And for 10 dB, it's 40 degrees difference for the antenna and -80 to +45 for the total input temperature. So it can be seen that there's definitely some large, if you have 10 dB reflections, which at some frequencies UWB-RAD did have 10 dB reflections, phase change. So at any time a phase would change, you can have a pretty significant impact on your calibration. Specifically for UWB-RAD, applying it to our internal calibration testing, when we have liquid nitrogen testing, we characterize the test fixture and attach it to the UWB-RAD's input. And if you were to just use a simple reflection model and assume only treating reflections as a loss compared to the multiple reflection model, there's a pretty significant difference of up to 40 Kelvin that could be had during internal calibration. So it's important that you use this multiple reflection model if you have high reflections. This is a stop band here and isn't really relevant for this. In addition to this, there's also uncertainty. When you do characterize that test fixture, your network analyzer is going to have some uncertainty in its measurements. For the particular one that we used in our lab, these were from the specification for it. As the magnitude of your reflection decreases, the phase uncertainty increases. And for UWB-RAD specifically, we had about plus to minus 5 Kelvin uncertainty in our internal calibration testing, just as a result of the phase and magnitude uncertainty of our network analyzer. So some possible remedies, now that you know that phase changes could be a problem, what do you do about it? Incorporate your measurement uncertainty into your calibration tests. You can try to reduce reflections with isolators, but as you go to wider bandwidth receivers, it gets harder and harder to find these isolators that are good over the entire band, and they increase your loss, reducing your sensitivity. Frequent calibration of at least 2 external targets. So some higher frequency radiometers already do this. They have built-in external targets that they can view. For us, we were on a plane. We had a very low frequency radiometer. We're down to 500 megahertz and with a pretty wide beam width because we were looking at such a wide bandwidth. So it was hard to get 2 external targets for us, but future radiometers should try to do that. And just, standard extra vigilance to keep the system stable in temperature and in your configuration so that you can keep phase changes to a minimum. So in conclusion, multiple reflections can't be ignored. Even when you have down to minus 30 dB reflections, it can still have a up to one Kelvin or more Kelvin effect on your response. Moving to off-the-shelf solutions instead of custom solutions, you're going to have to compensate for impedance mismatches. So this is going to be part of calibration procedure. Always incorporate your network analyzer measurement uncertainty into your calibration testing, and try to have external calibration and stable systems so that to reduce the potential of phase changes happening in the first place. So thank you for your time.
Okay, thank you, Mark. Does anyone have any questions? You can, again, unmute yourself or put them in the chats. There might be a delay, so I did have one question while we're waiting to see if anybody has any others. How different are the mismatches for a wideband radiometer as opposed to a more traditional narrowband radiometer? What is the main difference?
Yeah, so so as you have a bandwidth of a filter or an antenna, as that increases, your reflection pretty much has to increase as well. So for UWB-RAD, our antenna, we had a minus 10 dB maximum spec that was applied to the antenna. And it did hit it at some frequencies, but overall it was lower at others. But many narrowband radiometers, you can try to tune your filters and your parts, your antenna, to get a very good match at the frequency you're observing. Whereas with wideband, you have less ability to do that at all frequencies. So it's going to be a higher reflection. Did that answer your question?
Yeah, sorry, I was just looking for the unmute button.
Yeah, no worries.
And a follow-up question to that, I mean, isolators jumped into my mind. I know you mentioned them in your conclusions. Does the signal flow methodology still work for non-reciprocal components like isolators?
I believe it should. I mean, I don't think there's in Bosma's dissertation, there was some talk about non-reciprocal devices and whether, so ideal isolators don't exist and how does that impact things. But I believe it should still be applicable even for a non-reciprocal device. I'm not certain, I'd have to look into it more, whether the outgoing noise waves from each side have the same correlation and everything. But I believe that definitely the model should still be applicable. The signal flow graph model is what it is. Whether the values are the same as what we would use for a reciprocal device, those might need to be changed. But the model itself should be applicable no matter what.
Okay, thank you. Any other questions from any of the attendees? You can use either the chat of the WebEx or the chat of the YouTube as well as trying to unmute yourself.
Yeah, I see a comment from Adriano in the thing here about your isolator question. So it sounds like he actually covered this a while ago, and it sounds like it is a passive network.
Okay, great. Yeah, I seem to not be able to see the chats. Okay, I guess then if there aren't any other questions, we'll move ahead to the next paper. Thank you, Mark. Very interesting presentation. Our next presenter is Vince Leslie. Vince, if you could share your screen. Okay, we see your screen.
Great. And can you hear me okay?
Yes, sounds good. Go ahead, please.
Sounds good. I'm Vince Leslie. I'm the instrument scientist on the Tropics mission, and I'm going to talk about our TVAC calibration. Bill Blackwell had some great slides and presentations this MicroRad on the Tropics mission, but to remind people how small our CubeSat, it's about a little over a foot long, and we have a cross-track radiometer in the front, the 1U, and it has channels at
Vince, your audio is fading in and out.
Okay.
Now you're back.
And so we use the typical, as you can expect, periodic absolute calibration. We have a nonlinear response between the radiometer radiance, and we do typically done by deep space as the cold point.
You're still fading in and out. You're mostly out.
Yeah, I guess I'll try to speak louder, but there's not much more I can do. I don't have my video on. How's that?
Yeah, go ahead, please.
Okay. And it can be difficult to shield those targets, but we are mainly limited by size and weight. So we instead noise diode after the antenna to characterize the. I want to take the time just to place where this presentation is in the algorithm. So we have the upwelling radiance, which is converted by a total power radiometer geometric counts, but needs to be calibrated back into an estimated radiance. And typical of cross-track radiometers, we have the rotating payload, which measures the Earth. But for our warm target, we turn on the noise diode and measure deep space with the noise diode on, turn it off, and then measure deep space later on. We also have a typical calibration equation where we have the gain and offset, but we also have a nonlinearity correction. Now, unlike traditional that characterize the nonlinearity in TVAC calibration, we also have to calibrate the noise diode using our calibration test setup. So in TVAC calibration, besides that characterization, we also have to verify our requirements, our random noise, NEDT, and calibration accuracy, and also noise diode stability. We put a lot of effort into our calibration apparatus. You can see it in the upper right there, where the payload's in the middle, and we have the external targets surrounding the rotating payload. We have a picture of the support equipment and temperature controllers bottom right. Now, a lot of effort was made in this. There was a lot of progress from the MicroMass 2 days for us that we have put significant effort to minimize the error sources. So the plot on the right here is the PRTs or temperature sensors that are in one of the targets. There's 8 of them, and they're spread out in the back of the target. And this is one of our colder calibration temperatures that we go to. We don't try to push it down too much further to minimize the gradients. And we have some really good results from our end-to-end calibration. The other way of looking at it to see the overall accuracy of our setup is to look at these 3 linear channels. So I have one from each of our bands here. And so we have the accuracy between the PRTs, equivalent radiance, and our calibrated radiance using the external targets. So no noise diode here, no nonlinearity correction. We just wanted to look at the raw accuracy across the different scene temperatures. And we can say that we feel that we're about maybe 0.1 to 0.2 Kelvin accuracy with this test setup. So we think that we're very successful in minimizing the error. The other part of the design is that we kept the calibration targets in the same kind of angular space that we were going to see on orbit in order to test as you fly or calibrate as you fly. At first, we did the traditional technique where we kept the payload very stable, and then we moved the variable target or the scene target through the dynamic range. And I have some results from early on that. We have in the upper right here, we have the accuracy over the different scene temperatures, and you can see the deviation per temperature. We started to get nonlinear. We had the maximum deflection that we talked about. So that was used as a parameter to correct for. The bottom right is the noise diode temperature over the physical temperature of the sensor. And you can see the bunching of the 3 different temperatures that we chose, and we went off and we did a parabolic fit to that. So now we took all of that characterization and then did an accuracy measurement, residual accuracy in the left hand here, and we were able to reduce most of the nonlinearity to requirements. But it turns out that this wasn't comprehensive enough. We needed more to do than just stable temperatures. Unlike ATMS that is temperature controlled, we are going to have some pretty wide swings, plus or minus 4 degrees C in an orbit. And so we had to look at the hysteresis possible hysteresis as we changed the temperature of the payload. And we found that we did have hysteresis, and we corrected in a few ways. One, we had to make some hardware changes. Two, we had to do some screening and burn-in of the diodes. This is a very common finding across all the other programs. And we also had to find different telemetry that might better represent the data. So maybe you have a temperature sensor that's not exactly on the proper component, it's separated. And so we might have had to use some other different telemetry. So through trial and error, we came up with two profiles. We call it a characterization profile that had a high temperature rate change and a wide temperature range that we used for characterizing, and I'll show some results next. But we also made a verification profile. We didn't want to use the same thermal profile. We wanted something closer to our on-orbit simulation, so the dashed lines are our on-orbit. So we made this very comprehensive verification profile. So first, here's some quick looks at some of the panels that were easily parameterized by payload temperature. On the left is some noise diodes for the F and G band. We don't have those three distinct spots or temperatures. We have dynamically changing. Now talking about the verification. So on the right is a movie of the payload turning inside the calibration apparatus. And just to remind you, we placed those in a certain section so we could test as we fly. We had the noise diode turn on just before it hit the target. And here's some example data that we had, where on the Z-axis we have antenna temperature, and Y is angles, the 360-degree rotation, and then scan index is just a new rotation. So you can see on the far left that we had a turn-on transient of the noise diode. It settled quickly. That's the point where we collect the warm part. We then, 120 degrees later, were able to get a cold measurement, and then we did a scene target, a stable scene target of 250. Before I go into the results, I want to talk about a comparison of these two, the so-called traditional and the new dynamic one. There's a lot of benefits for a CubeSat that is not temperature controlled. We had a wide range in the valid verification data set. It was changing physically in time. We checked the comparison or the characterization of the temperature and the nonlinearity throughout the instrument temperature. So not just at one. The only drawback is that we didn't have range. It was too hard to move that dynamically and to keep the gradients down. But we were able to confirm that the nonlinearity was parabolic and completely explained by our correction term.
2 minutes.
Thank you. The results here are from 7 hours of that verification profile, where on the x-axis you can see the payload temperature was constantly changing, and then we have the accuracy against that 250 Kelvin target. Now, this is some very unique data. This is some of the first that we've known where the entire space vehicle with the payload was calibrated. Now, there's definitely space vehicle testing, but we did a full calibration of the payload. And furthermore, we had the payload calibrated in March of 2019, and then had it go to BCT, integrated onto the space vehicle, and returned to us about 9 months later, which is only about 6 hours of being on. And we were able to recalibrate it with the space vehicle in the same calibration apparatus. So that's unheard of as far as we know for a passive microwave radiometer. The two different curves here are all space vehicle cal in December, but if you apply the calibration 9 months earlier, you get the green curve. And then if you apply the calibration when the data, approximately when the data was taken, you have the blue curve. And so the differences here are being attributed to noise diode change, and we have an elaborate on-orbit biasing scheme to measure this difference and to wrap that back and feed back into a calibration correction so that we can minimize our bias. Quickly, we also have the NEDT, or the precision. This is the worst case. So this is histograms of 7 hours worth of data where you have that bias moving around, and we were able probability density function and pull these off. So this includes all the flicker noise, all the thermal noise, and all the calibration noise. And so we meet. The other very important thing with the noise diode is the stability. And we have a metric on each of these. Not only will we be taking all of the space vehicles out of storage when we finally get a launch. We will be also recalibrating. This is a metric that was done within the calibration over a few days. We looked at the two characterizations. Used up all my time, so I'll end here.
Okay, thanks, Vince. If anybody has any questions, please go ahead and either unmute or put your questions in the chat. While we're waiting for questions, I think the first question that comes to my mind is, since you're familiar with more traditional radiometer with KTMS, what was the single biggest difference that you think you faced in terms of trying to calibrate either one?
I think it had to do with the temperature stability, that we are temperature controlled in KTMS, and the big challenge was that we are not temperature controlled with these CubeSats. Obviously, the noise diode totally replacing the match or the internal calibration target is one of the
Yeah, Vince, we're still you're still kind of fading in and out on your audio, but I think we got most of your answer. Are there any questions from the audience? I'm not really seeing anything in the chat. I'm not sure if my chat is somehow stuck. So if there's anyone in the audience that has a question, please try to unmute yourself. So another question is, you probably mentioned this near the beginning of your talk, but it would be good to maybe repeat it. What's the schedule for getting Tropics in orbit?
Sure. There's an outstanding launch request for launch providers that are probably coming up, I think, in a month or so. And the Pathfinder, which is the qualification unit, will be launched off of Falcon 9 this summer. So we'll have the Pathfinder, a single satellite data, hopefully this summer.
Okay, great. Any differences or similarities in the calibration of the predecessor MicroMass compared to Tropics?
That's wrapped in a lot of lessons learned. We had, for example, a direct detect system for G-band, which allowed us to help with some RFI. So when you make an instrument this compact, you have to worry about crosstalk. And so going to the direct detect kind of separated the IF. We obviously have no IF in G-band anymore. And so that was a helpful upgrade. We also are co-located beams. So instead of having 2 feed horns hitting a reflector, they have the wire grid that will make them more co-located.
Okay, again, I'm not seeing any other questions, and I'm a little concerned. It might just be that my chat window is kind of frozen.
Maybe we just had a good talk together then.
Yeah. One last quick question is, if you had to design if you were given a little bit larger volume to work with, what might you change?
I guess if we did go to a larger volume, it wouldn't hurt to have more calibration points. If that would be more like a matched load and noise diode, and or an external target, and have consistency across all of them.
Yeah, interesting. Okay, maybe if I'm still not seeing any other questions yet, so perhaps I'll thank you, Vince, for a very interesting talk and some great work by the team there. I think we're all interested.
Yeah, definitely a big team effort.
Yeah, where I think, you know, many people will be very interested to see data coming down once you're able to get in orbit. And I'll turn it over to my co-chair, Andreas Scoliando.
Ed, so let me introduce the next talk. Speaker is Ed Kim. The title of the talk is Pre-Launch Performance of the Advanced Technology Microwave Sounder on the Joint Polar Satellite System 2 satellite. Go ahead, Kim. Ed.
Okay. And are you able to see my slide and hear me okay?
Yep.
Okay.
Yeah.
All right. I'd like to acknowledge a long list of co-authors, including the previous speaker. And as well, we have colleagues from Northrop Grumman, the manufacturer of ATMS, and colleagues at NOAA. This was also a large team effort. On this second slide, you can see a picture of ATMS, and this was to say all the ATMSs are built by Northrop Grumman. They are the microwave sounder. They provide temperature and humidity profiles, and the instrument flies as part of the suite of instruments on the JPSS satellites. So according to the usual tradition, those satellites are numbered, you know, JPSS 1, 2, 3, 4, prior to, during all the pre-launch activities. I think there's an automatic timer, apologies. And once they get on orbit and the commissioning is successful, they get turned over and renamed by NOAA. So the two that are in orbit right now are the first ATMS launched on the SNPP satellite back in 2011. The second ATMS is now on NOAA 20, which launched in 2017. And this paper is going to focus on the third ATMS, which we expect to launch maybe sometime later next year. There are 22 channels that cover the usual sounding frequencies, starting at 23 gigahertz, going up to 183. And as I'm sure other speakers, many of you are aware, these microwave sounders provide very high impact observations for the operational weather forecast agencies all around the world. Every 6 hours, those NWP centers are generating weather forecasts that use the information from instruments like ATMS. So we've selected in this presentation about a half a dozen performance parameters, measured pre-launch characteristics of this third ATMS unit. So the first performance parameter is sensitivity, or noise equivalent delta temperature. And in this plot, the x-axis is the channel number, and the y-axis is the NEDT in kelvins when viewing a 300 Kelvin target. So this includes both white noise and 1/F noise contributions. What you'll see here, the different color bars represent the 3 different flight units that were mentioned in the introduction. And you can see slight improvements. Generally, both the JPSS-1, which was renamed NOAA 20, and the JPSS-2 are doing better than the first unit. And in addition, on some of the channels, for example, channel 17 through 22, you can also see some improvement between the JPSS-1 and JPSS-2 builds. The other thing you'll notice is that overall, there's consistency among the 3 builds at any of the individual channels. That's good. You know, the design really hasn't changed significantly, and the components really haven't changed significantly. So you would expect to see consistency like that. On this slide, you can see some plots of the interchannel noise correlation. So channel numbers on both the X and Y axes going from 1 to 22. And the first plot on the left, and the color scale is the correlation itself. So Ideally, you would want all your channels to be independent and have zero correlation. So ideally, except for the diagonal, you should see that dark blue color. Any place you don't see a dark blue color means that you've got more correlation between those channels than what would be ideal. So when we launched the first unit, the SNPP ATMS on the left, we discovered that the V-band channels, which are the light blue colored ones in the lower left corner of that plot, as well as the G-band channels, which are in the upper right-hand corner of the plot, had significant interchannel correlation, a lot more than we expected. Certainly got lots of comments from our NWP users. When we launched the second one, which is the plot in the middle, we were happy to see that significant interchannel correlation had reduced quite a lot. There's still some correlation there between channels 18 and 19, and a little residual up at the G-band channels. But overall, you can just see visually that there was a significant improvement. And then on the far right, you can see the interchannel correlation for this third unit. And again, you can see even some additional improvement, especially at the higher channel numbers, the higher frequencies, a bit more improvement at the V-band. So we're very happy to see this, and I think our NWP users would be very happy also to see that they should have more independent information content. Now we come to striping. So the image in the middle is an example of striping. What you see along the x-axis is basically time or scan number, and on the vertical axis, this is the cross track or beam position. So so the x-axis would also be sort of like a long track, and the colors indicate sort of relative power that you're seeing while the satellite is flipped upside down. So during commissioning, we do a number of tests, one of which involves flipping the entire satellite upside down, which gives us the opportunity to look at cold space, which should be cold and uniform. And so the fact that you can tell from the colors, you see these vertical stripes of red and yellow colors instead of seeing a nice flat sort of blue color all the way across, indicates that we're seeing something other than a nice flat field. This is traced back to the 1/f portion of the noise power spectral density, and as you saw in the previous slide, this striping impact is reduced compared to the previous units. I'll note that you can make the image look worse or better just by what colors you choose. So don't want anybody to think that this means that the next ATMS is going to be horrible in any way. Literally, you can make this look as good or as bad as you want just by changing the colors. The important thing is probably from the previous slide that we would expect. I'm sorry, from this, but also in the next slide, I'll show that we do expect a reduction in the striping. So let's go to that next slide. As I mentioned, the source of the striping does derive from the noise power spectral density. Here we see plots of that noise power spectral density for two different channels. We just picked these to highlight the differences. The different colors show the different builds. So the blue color represents the first ATMS, the pink color represents the second ATMS, and the red color is this most recent ATMS. And you can tell that, especially in the left example, which is for channel 19, you'll note that the first two ATMSs, their noise power spectral densities were almost identical. They pretty much overlapped with each other. But as you can tell from the red dots, the noise power spectral density for this third ATMS is considerably better or lower at this particular channel. So that's an example of a channel where we would expect significantly less striping. On the right, for channel 6, again, you can see that the first two ATMSs had noise power spectral densities that were quite similar. And if you look at the red dots for the third ATMS, it's got less 1/f noise and less noise in the white part of the power spectrum compared to the two previous ones. But certainly it's not as much of an improvement as you see for the channel 19 example on the left. So that channel 6 would be an example of a channel where we would expect a slight improvement with respect to striping, but not as much as we would expect to see for channel 19. So
2 minutes.
Thank you. This next plot, this is again, the 22 channels on the x-axis and the predicted accuracy in kelvins on the y-axis. These are a combination of both measured and estimated numbers weighted according to an error model. The takeaway message from this would be that we have very good consistency among the 3 builds for all channels. Here we show some antenna-related measurements. You can see the beam widths, measured beam widths for the different 5 different bands, as well as the main beam efficiency. These are all meeting the requirements, so we're happy to see these numbers. And in conclusion, we expect that based on these pre-launch performance characterization data, that this next ATMS will meet all of the mission science needs. Performance is consistent with the previous builds. There's some slight improvements in various areas that we highlighted. For example, definite improvement in the NEDT for the G-band, improvements in the interchannel noise correlation, and less striping. So we will, of course, be doing additional tests before, primarily once we get on orbit during commissioning. And we'll be happy to take any questions. Thank you.
Thanks, Ed.
Yeah. Ed Algashevsky, I've got a question. To what do you attribute the reduction in interchannel noise correlation?
Hi, Al. Excellent question. We've been asking that ourselves. Obviously, there are, the fundamental source of that is shared components in the hardware. And why from one build to the next, there was a reduction. The components haven't really changed for most of the channels. There were a couple channels where just because vendors, you can't over the 10-year span between the first build and the third build, some of the vendors, parts are no longer available. But we don't necessarily understand why that would, directly translate into what we're seeing. The basic hardware design, at the block diagram level is identical for all 3 builds. So it's hard to say.
Yeah, thanks, Ed. Good, careful analysis, though. I appreciate that.
Other questions? I have one a little bit more generic question. So these instruments have very long heritage, this kind of atmospheric sounder. So what are the sort of the more broader or longer term trends in the instrument technology that you see, like
well, that's a great question. So one thing that is worth noting, the original the ATMS design is 20 years old. So for example, there's no LNA at the 183 gigahertz band because 20 years ago that wasn't realistic, especially for an operational instrument. These days, if you're going to build a 183 gigahertz radiometer, even an operational system, you would almost certainly put an LNA in there. The technology is definitely available. So there are things like that that are clearly, you would do differently. And then there are things that are the same because they're limited by physics, like the footprint size. The choice of frequencies is set by the physics of the Earth's atmosphere. You're not really going to go and use a totally different set of frequencies. The orbit altitudes are, you're always talking about the same range. And then it just boils down to, how big of an antenna you can afford to fit on your instrument or on your spacecraft. So when you think about CubeSats, for example, that's certainly one of the large differences between performance.
Nice, thanks. Okay, let's move on unless there are more questions. Thanks, Ed. Okay, next talk is by Giovanni De Amici. The talk is titled SWIRP, Development and Characterization of a Sub-millimeter Polarimeter for Ice Cloud Investigations. Go ahead, Giovanni.
Good afternoon. I hope you can hear me and see the screen. If not, please holler. I'm going to report on the latest and unfortunately very small progress in the development of the SWIRP, a sub-millimeter wave and long-wave infrared polarimeter for studying the top deck of ice clouds. SWIRP is a small instrument, is not a CubeSat grade instrument. It takes about 12 CubeSats to fit it in. So we're more in the small sat regime, but is also suitable for flights of opportunity on other platforms. It's the concept behind. Oh, come on. Okay. The concept behind SWIRP is to study the ice distribution in the clouds. Clouds are an important parameter in climate, but they're also still relatively unknown and poorly understood. They control very much the heat exchange, controlling the albedo and the reflection of heat from the ground. Ice clouds also affects local weather. On the top left, there is an example of the precipitation forecast with and without the inclusion of ice clouds in the modeling. The ice clouds tend to be at high altitude, where we have very little information from radiosones, and they are cold. So one important aspect of the ice particles inside the cloud is their size and it's their orientation. So we're developing this polarimeter instrument, which is going to use two RF channels, well, sub-millimeter channels at 220 and 680 gigahertz, and one polarimetric infrared channel at 10 micron approximately. The spectral band of the 220 is about 12 gigahertz. At 680, we use 20 gigahertz bandwidth, and at in the infrared, we're using approximately 3 micron, 8.5 to 11. I'm not going to discuss the infrared component because this is a microwave specialist meeting. It is being developed by the University of Arizona, while the sub-millimeter receivers have been developed in terms of hardware by Northrop Grumman in Redondo Beach, California. we need to go to infrared and we need to go to sub-millimeter because ATMS, an instrument like ATMS, like the one that Kim was discussing, only sees the top 5, 6, 7 kilometers, the bottom 5, 6, 7 kilometers of the atmosphere. We are interested in seeing something that is at a 10, 15 kilometer altitude, and the optical depth at those altitude is ideal for using infrared instruments, and sub-millimeter is not suitable for using microwave instrument, which is unfortunate because microwave instrument is something that we understand very well and we know how to make. These higher frequency devices are a little less defined. The SWIRP is playing a role in the decadal survey. It's also trying to establish the record of being the first small instrument that carries both sub-millimeter and infrared instruments on one platform, although at the rate at which process is going, somebody might beat us to the punch. We are well connected to the 2017 Decadal Survey. We're going to provide critical information on the distribution of aerosols in cloud, and we want to do that so that we can inform prediction and assessment of climate change. The idea is that the instrument, which is small, you can see it here, it's about 20, it's a drum 20 centimeter in diameter and approximately 37 centimeter tall at its highest point. We're going to fly on, we hope, on a polar orbit so that we can cover the whole planet. It's going to be a scanning device along the lines of WINSAT or CIMIS. We're going to have a field of regard of about 160 degrees left to right. And we're in the back, and if you can see my cursor, I'm going to point to it. We have what we call a calibration wall, where we're going to install 2 external black bodies, this being one, for the sub-millimeter instrument. One of the black bodies will be kept at ambient temperature. The other one will be kept at about freezing or above freezing temperature. So to give a wide range of temperatures for the calibration of the instrument. A third calibrator, hot calibrator, mounted around in this area will be used as a source for the infrared. Oh, I better speed up. Okay. The observation geometry is very simple. 400 kilometer orbit, 36 degree angle from nadir. We scan about 17 times a minute, and we have a field of view of 30 by 20 kilometer at 220 gigahertz and 15 by 7 kilometer, excuse me, by 10 kilometer at 680 gigahertz. That means that we need 2 680 gigahertz receiver to cover the same ground. And indeed, we have 2 of those. So 4 channels at 680. Yes, 2 minutes. Thank you. This is the field of view of the instrument, of the sub-millimeter instrument projected on the ground. Nyquist sample, so that we should have full coverage. Let's skip this. These are the data from the antenna as built, and they show that we meet the requirement. The instruments, that's where I wanted to get. I was hoping to get some lab test results for these, but we got hit by the pandemic. This 220 gigahertz has been delivered. The 680 gigahertz met some difficulty in final testing, It is still an auto requirement, not because it needs work, but because the receiving dock at Goddard Space Flight Center was essentially shut down by the pandemic, and we cannot receive it. It's there, it's working, it's going to be great. Volumetric performance is as good as you can hope to get it, actually better. And E delta T is meets the requirement, greatly meets the requirement at 220 gigahertz. It's sufficient for the measurement. So the requirement was better than half a Kelvin, and we are very close to it. Not much to spare. The NE delta T is calculated under realistic conditions of observation, 10 millisecond integration, which is what we're going to do, 10 gigahertz bandwidth. Our timeline, greatly stretched now, is we're going to hope to get back into the lab in winter of the next few months. We want to go to some rooftop validations during the summer, not the ideal time in Maryland. We're going to have a lot of humidity and very little ice clouds. And then we hope to get some engineering flight. Ooh, those dates are wrong. So spring for rooftop validation and summer for some engineering time, hopefully on a year 2 platform. And then the engineering model will be done, and we hope to be able to get into some real flight device. And I think I'm out of time, so questions, please.
Yeah, thanks, Giovanni. Questions to Giovanni? You can unmute or post them in the chat.
Okay.
So I have one question regarding this kind of general question. How does the system parameters compare to, for example, the ice cloud imager ESA is developing or has developed for their METOP series?
This is a much smaller instrument than what ESA is proposing. Our main reflector is only about 12 centimeter in diameter. So while
and how about in terms of, sorry,
I'm sorry?
Yeah, I was wondering, and how about in terms of like frequency selection and those kind of?
Frequency selection, we have about the same. Everybody's working in the same frequency bands.
All right. Yeah.
There is some good reason to work at those frequencies. At 680, we have there is a window between ozone lines that is pretty much forced on us.
Nice. All right. Thanks, Giovanni. I don't see any other questions.
Going back on mute.
All right. Okay, let's see. So next presentation is by Rachel Kreutzma. The title of the talk is Recent Activities of the GBM in the Calibration Working Group, XCAL. There we go.
All right. Oh, wait, I'm not sure if that shared.
Yeah, we can see it. Yeah.
Oh, can you see
Maybe
the PowerPoint?
Yeah.
Okay, it looks different from when I attempted in. Okay, and then I'll switch this. Okay, so you're seeing the proper slide,
Yep.
not the presentation view?
Yes.
Perfect. Okay. Welcome everyone to the last talk. Thank you for sticking around. I appreciate it. So my name is Rachel Kreutzma, and I will be presenting on recent activities of the GPM Intercalibration Working Group, or as we're more commonly known as XCal. And my co-authors there are Wes Berg from Colorado State University. He is the lead of our XCal group. And we have Linwood Jones from the University of Central Florida, and he has a research group doing a lot of work down there. And then also Tom Wilhite, currently with the University of Maryland, ESSEC, is also doing work with us, and various others from XCal that have contributed to this as well. Sure. There we go. Okay. So for those who don't know, so the GPM Intercalibration Working Group, we're a group within the precipitation measurement missions. This is what we call collectively TRIM and GPM. So Tropical Rainfall Measuring Mission, which was decommissioned in 2015, and then the Global Precipitation Measurement Mission, which launched the GPM Core satellite on February 2014. So our XCal group, we are responsible for the level 1C intercalibrated brightness temperature files. And these are what get input to the operational precipitation retrieval algorithm, which is known as GPROF. And so that's what we are responsible for. And so we actually existed for several years prior to the launch of the GPM Core satellite. We were spending many years developing our algorithms, working on sort of a process for what we would do once the GPM Core launched. So here I just have listed some of our activities that we've done since the GPM Core launched. So back when GMI was launched, we assessed and updated the calibration for that sensor and brought it up to the current version, data version that you can download. It's called version 5. And then we also intercalibrated the radiometers that were currently in orbit, and we intercalibrated those to our calibration standard, which is GMI. And so that actually took a lot of effort. You can see our paper reference down there on the bottom. There's many names there that that worked with us back then. And after that, we kind of XCal decreased in size a little bit. We still had a lot of work to do after TRIM was decommissioned in 2015. We reprocessed the entire TMI data set going back to when it was launched in 1997. And we updated the TMI calibration and then also intercalibrated TMI to the GMI. And then we gathered a bunch of other radiometers that were in existence during what we call the TRIM era, back when TRIM was in existence. And we intercalibrated those to GMI and created a long-term data set. So it brings us up to where I'm going to talk about today, which is some of the recent kind of in the past couple of years that we've done, is that we then went further back in time and extended our constellation back to July 1987. So we have a continuous data set dating all the way back from there to the present of microwave radiometers. And then things that we've also done recently is incorporate new sensors, for example, the NOAA 20 ATMS and also the METOPS EMHS. We were launched since the launch of GMI, and we added those to the constellation. And then some of the stuff that's in progress is we have a new version of the GPM dataset coming out approximately mid-year, mid-2021 of next year. And so we've been updating some calibration for that. If you heard a talk earlier by Alamgir about new TMI, that is included in that version. And then we just have some ongoing things that we've been doing over time. So here is the current status of our GPM constellation. So you can see on the left here, we have conical scanning radiometers as well as cross-track scanning radiometers. And these, the frequencies, the center frequencies for these instruments goes from about 10 gigahertz up to 183 gigahertz. So it's frequencies that are optimized for precipitation retrieval. So we have 5 current conical scanners there that you can see listed. And then we had a bunch that have since been decommissioned. And then we have 6 current sounders that are in our constellation. One of the things I'll note here is that several of our current sensors have been operating for more than a decade. And so some of these have had channel failures over time or just increased noise. And those affect our our intercalibration will affect the precipitation retrieval. So we continue to monitor the instruments for those issues. So one of the first things I'll talk about here is you can see on the left with the conical scanning, you can see where TMI is the green bar that goes across the middle there. So you can see there are two SSMI instruments, F8 and F10, that did not overlap with TMI. And so recently we intercalibrated all of those that matched up with TMI in time. So that was F13, F14, and F15. We had to go back and get the other SSMIs. And so that's what I'll talk about first. What we did a couple of years ago, we have a paper reference there, is we extended the constellation back to July 1987. And in the process, we actually updated some SSMI calibration, and which included the pointing parameters. You can see on the left, roll, pitch, yaw, and the half cone angle, as well as we updated some along scan bias correction, which includes some edge of scan. You can see there that certain channel has some edge of scan obstruction right there that we correct for, so it doesn't appear in the final data set. And up there on the left is so one of the things you can do to see if you are pointing in the correct direction is if you take the difference between your ascending and descending orbit brightness temperatures, coastlines will light up if your pointing is off. And so you see there at the top three panels there, you can clearly see Australia is light up, and then the bottom three panels are what we ended up correcting for and what the final geolocation was. All right, so another thing that we do is we add new sensors to the constellation. So this example here shows when the NOAA 20 ATMS was launched. We actually just heard a talk by Ed Kim talking about the ATMS instruments. So we had to add this one into our constellation, which requires calculating intercalibration tables. So it's a double difference method we use, and so we correct we intercalibrate the brightness temperatures to be consistent with our calibration standard, which is GMI. And so here just shows a table of three different methods that are used. So it's I came up with some constants, Westberg, and then you can see Tom Wilhite. We each have different methods we use to intercalibrate the instruments, and when we get consistent results among all our methods, it gives us confidence that we are doing the right corrections. And so we actually take the average of those, and then so that's how we add an instrument to our constellation. So I'm not going to spend much time on this. Alan Garrett talked about this earlier, some updates that he was doing, and this includes some updates to the TMI emissive reflector. And so he's done some great work on coming up with a new improved table to account for the emissive reflector on TMI. And those new corrections will be included in the next version data release. All right, so the other thing that we are doing is that we are updating the SSMI-S dataset. So this is Special Sensor Microwave Imager Sounder. And there are 4 of these sensors that were launched on 4 different platforms. 3 are currently still in existence. And so we have decided to update this for the next data release because the last analysis that was performed on the current data that we have was almost a decade ago. And so that means we have a lot more data since 2011 to use just to give us more confidence in the results that we have. Also, there's just been recent algorithm improvements. We just have greater knowledge of how to analyze calibration issues with the instruments. And especially we did a lot of work on SSMI, which I mentioned recently. And some of that work indicated that SSMIS would benefit from doing a reanalysis similar to what we did with SSMI. So one of the first improvements we looked at was sensor pointing parameters, like I mentioned earlier with SSMI. So we updated those. We also did the cross-track bias correction to remove edge of scan obstructions. And then the third thing that we're working on with SSMIS that was not an issue with SSMI is what we call a sun angle correction. And this is to account for a known emissive reflector that SSMIS has, as well as some warm load solar intrusions. So first, I'll show here the geolocation improvement. So this is updating the pointing parameters, like I mentioned, roll, pitch, yaw, and half cone angle. So you can see on the top, so this is actually, you can clearly see that the Iberian Peninsula there is very lit up. So this is using the F-17 platform SSMIS. Thank you. And so you can see the fact that you take ascending minus descending brightness temperatures, and the coastlines lighting up indicate that the pointing parameters are off. And so we're able to use this idea here and back out essentially the pointing parameters. And so you can see on the bottom there, the coastlines have essentially disappeared in our new data set. Okay, and then finally, like I said, we call this a sun angle correction. So on the top left, there is a time series of one of the channels on F-17. And so each of those lines represents, it's a single difference anomaly. So it's a observed minus simulated brightness temperatures, and it's an anomaly of that. And this is split into ascending and descending orbits. And they should essentially be flat, and they should definitely not have such a large difference in between them. And so that is an indication that there is something wrong in the calibration. And actually, if you filter that single difference anomaly into sun azimuth and sun elevation angle, so it's a sun position relative to the spacecraft, you can see the pattern that appears there on the bottom left. Very large differences. So, you know, about 10 Kelvin peak to peak, which is an extremely large calibration issue. And actually, if you plot the mean reflector temperature, this is for F-17, there on the bottom right, you can see a pattern, a very similar pattern emerge. And basically that is essentially due to having an emissive reflector. The fact that you get your brightness temperatures to change because your reflector temperature is changing as the spacecraft is going in and out of eclipse. And so that is something that we need to correct for. And so we are working on updating this. This correction had been in the previous version, but we also, like I said, we have about 10 more years of data than what we had back then, which allows us just to get better statistics on our analysis. So that's what we are currently working on. So I will end here with my summary, just saying that we have done extensive work on analyzing the calibration of the GPM constellation. So we've improved several sensors and intercalibrated them all to GMI. We're currently working on the calibration improvements in preparation for the GPM version 7 data release, including the TMI emissive reflector, and then the SSMIS corrections listed there. And as I said, we are the XCal group has definitely decreased in size in recent years, just because we do not have as much work as what we did right after GPM Core was launched. And right now it's just kind of monitoring current instruments, adding new ones when they get launched. And definitely, as we've seen this week, there's some exciting new instruments to be launched in the next several years, and that we would hope to add into our constellation. Things like quantifying uncertainties and just improving our current algorithms, and working with the GPROF level 2 precipitation algorithm to improve the calibration of our instruments. So thank you.
Thanks, Rachel. Questions to Rachel?
Rachel, this is Al Gashevsky. Good work, and I'm glad you're doing this so carefully. Thank you.
Thank you.
My question is on the roll correction, what was the source of that error? Was that a bias in the platform? Was it somehow a bias, stack-up bias in the instrument? Or what?
So it is really difficult to figure out if it is due to the instrument alignment or the spacecraft alignment. We just don't really have enough information to separate those two. And so we have actually just said that it is a sensor roll offset. You know, we've looked at like we can derive, you know, roll pitch offsets over time. And so we've looked at a time series of those over time. And while we see, you know, some slight variations in that could indicate that it's due to a spacecraft issue, we've kind of just decided to roll the, you know, it's a fairly small error. And so we just assume it's a constant roll offset for the entire mission is what we derived.
Mm-hmm. Yeah, thank you.
Other questions?
Mm-hmm. I cannot see the chat if anyone's right. I don't know what happens to my chat when I share the screen. I don't.
All right, yeah, but yeah, no, there so far we don't have any on chat.
Okay.
Andreas, this is Ed. I have a good question for Rachel.
Oh.
Yeah, hi Rachel. Thanks.
Hi Ed.
Great work. Since everything is tied to GMI, if GMI changes, then everything changes.
Yes.
How
essentially?
How often? I mean, can you say something? Or is there anything you can tell us about like what kind of quality control you do on just being aware of any changes of GMI itself?
Yeah, I mean, we monitor GMI just like the other instruments, and even though I say here we have a GPM version 7 data release, the GMI calibration is not changing. So that means that the other instruments, like say ATMS or MHS, the ones if you download the level 1C data for ATMS and MHS, they will not change with version 7 because GMI has not changed. We don't expect GMI to change. It's an extremely stable instrument, and a lot of the work that we did with it was, right post-launch. But yeah, that is, if something would happen with GMI, we would end up having to change then the constellation, or we might have to discuss at that point. We might have to say, well, do we keep the calibration standard what GMI, was or like is right now? Say if it changes 5 years from now, do we keep the calibration standard as what the current GMI is, or do we switch it? That would be a discussion for the future. But as of now, GMI is extremely stable and is not changing for the next data release.
Right. Thanks.
Great. Thanks, Rachel. So that concludes our session. Thanks for all the speakers and thanks for the attendees. And I'll hand it over to the organizers. Thank you.
So we are arrived at the end of this MicroRad 2020, the 16th MicroRad edition, and the first one, and hopefully also the last, entirely in virtual mode. The conference was held indeed on WebEx and also streamed on YouTube. Let me recap a few information about MicroRad 2020. We had talks in 13 different sessions covering 8 topics that deal with all the fields of microwave radiometry. On Wednesday and Thursday, we had 2 parallel sessions, and from Wednesday to Friday, we had 3 keynotes by representatives of the European, Japanese, and the United States space agencies. I would also recall the RFI discussion that took place as side event on Tuesday after the end of the last session. And last but not least, MicroRad 2020 hosted as a tradition the Golden Florin Award on Thursday, in which Niels Skov was awarded. Some numbers about the attendance. Despite the problems related to the pandemic and the consequent conversion to online event, we can say now that the interest in MicroRad 2020 exceeded every optimistic expectation. This was actually the reason for streaming the entire conference on YouTube channels. During the session, participants interacted with the presenters directly and via the 2 chats on WebEx and YouTube. And here are some numbers about the attendance. We can say that the streaming on YouTube revealed as a very good tool for spreading the conference and broadening the attendance, although we were not able to reach some countries like China, in which YouTube is not active. In summary, we had 88 talks because we recorded also 2 no-show. and about 300 registration between the presenters and attendees, and with an unknown new number of not registered attendants on YouTube, because after releasing publicly the link of YouTube, we lost any control on the attendance, of course. Here, just to give an idea, the geographical distribution of the co-authors of all the papers presented in MicroRad, we can see that most part comes from Europe and US, but we have also representative of other countries worldwide. The attendance was, as said, very good. This histogram shows the cumulative attendance between the WebEx in blue and YouTube in red. And we can see that we ranged between 100, 110 and 120 attendees for each session. We also recorded quite good attendance for the side event of RFI discussion, 45 attendees in this case. This is a rough average of the not updated with the latest numbers of today, but that is still, we arrived around 90 participants today also. Very surprising, by counting also the number of YouTube views, we had the confirmation that several hundred of people attended, or at least viewed the animation, the recordings on YouTube. We can see on Tuesday more than 500. More than 400 on Wednesday and Thursday, and these two numbers are still increasing because we have still the recordings of these 3 days on YouTube channel. I now leaving the floor to Marco for important information about the proceedings and special issue. Marco, please proceed.
Okay, thanks, Emanuele. So just a few words. First of all, thanking all of you who has attended this MicroRad, which since the beginning was really tough. It was really tough because of the pandemic and the reorganization of the meeting after March. So thanks all of you, thanks to the chair, and I will also want to thank Emanuele, which was my co-chair, and it was a pleasure to work with him. Just a couple of points to remind you is this one. It is possible to submit the 4 pages paper to be included in the conference proceeding. It will be published on, the proceedings are going to be published on IEEE Explorer. So if you want to, as for IGARTS, if you want to submit a short paper for the proceeding, you have the instruction here at this link. And you can refer directly to the website. And also, the other point is that IEEE starts approved a special issue on the microwave topics, on the MicroRad topics. So the tentative submission deadline is 31st of March of next year. We are going to send you a special advertises for this special issue as soon as the call for paper is issued. So make up your mind about contributing to the special issue, to the proceeding. I think it's worth to publish something in the special issue. So you have the floor, Emanuele. Thanks.
Okay, thank you, Marco. It was a pleasure for me too to work with you in organizing this conference. And now it's time to give thanks. As first, we would like to thank Paolo Ferrazzoli, that is the CITEM president. Paolo Gamba is the IEEE GRSS president. And Paolo Pampaloni as chair of the Golden Florins Award, and especially for being one of the organizers of MicroRad from the beginnings. Then we would like to thank our director of the Institute of Applied Physics, Roberto Pini, and all the local organizing committee, and here the list, Giovanni, Simonetta, and all the other people involved that supported us very strongly in all the technical and the practical aspects of realizing this online conference. In particular, a special thank to Patrizia Rossi. She operated behind the scenes, providing continuous and tireless support to us. I believe most of you interacted directly with Patrizia for questions related to registration, paper submission, and so on. And shall we try to switch on our microphone for a virtual applause? Last but not least, thank very much to the Permanent Steering Committee that well supported us with the practical aspects of the organization, as well as in the difficult decision on how to behave with the conference when the pandemic forced to withdraw the in-person event. And finally, thanks to session share, presenter, attendees, and all of you for your active contribution and support in MicroRad 2020. An applause again. Okay. I will now give the floor to Paolo Pampaloni for some greetings and then introduce the organizer of the next MicroRad in 2023. Paolo, the floor is yours.
Can you hear me?
Yes.
The audio is working?
Yes, it's working.
In the list of participants, I was included as a co-organizer. In fact, I did nothing to help the meeting, absolutely nothing. So, as independent observer, I feel free to express my total appreciation for this very successful edition of MicroRad. And as a past senior member of the Microwave Remote Sensing Group, let me express my congratulations to real organizers, first of all, the chairs Emanuele and Marco, sometime with Simonetta and Giovanni behind, and also to the coordinator of the Secretariat, Patrizia, as well as to all the other members of the group who, with different roles, participated in the management of a so complex mechanism. Everything has gone surprisingly smooth. So, again, congratulations and my best wishes for the next MicroRad. Thank you.
Thanks, Paolo.
Thank you, Paolo.
And thanks to all of the attendees. Without them, it was really, it would have been very tough and almost impossible, actually impossible, to have such a successful meeting.
Okay, so it's time to think forward to the 2023 edition that will be held in Washington metropolitan area, DC. And I will give the floor now to Ian and Rachel for some words about the next MicroRad edition. Please, Rachel, Ian, go ahead.
Hello. Thank you. We are extremely honored to be hosting the next MicroRad in the DC metropolitan area. We're working hard to really find a venue that is as intimate as this conference always is. I think one of the things we've really tried to do is reach out to a diverse organizing committee to really put together a great conference. Rachel, do you have any comments that you would like to add?
I'm excited to see everyone in person in a few years, and really excited to welcome everyone back to Washington, D.C. We were there in 2010, for those who remember. And so, yeah.
Okay, and I should note that to push us back to the sort of what's been the more spring time frame of the meetings, we'll be planning this meeting for March of 2023. Thank you.
Okay, so good luck, and if we can be of any help, don't be afraid to ask us.
Thank you. Thank you very much.
Thank you.
Yeah, see you in Washington in a couple of years.
Yes, in person.
Yes,
Yes.
hopefully. Yes.
Yes.
So this MicroRad has come to an end, but not to work. So we will look forward to see you at the next conference, MicroRad, or also project meeting, and it will be a pleasure to work again with you. So have a nice evening for those who are in Europe. Have a nice day for those who are in the US, and good night right now for those who are in Asia. So see you in a couple of years at least.
And do not forget about the proceeding and the special issue.
Ciao a tutti.
Bye bye.
Ciao a
Thanks
tutti.
for everything. Bye bye.
Ciao.
Grazie.
A presto.